Welcome to Sleepy Science Student, where we explore the universe's greatest mysteries one gentle breath at a time. Tonight, we're embarking on a slow, peaceful journey into the problems that have haunted humanity's brightest minds for centuries. Questions so profound, so elegantly stubborn, that even today's most advanced instruments and theories can't quite crack them open. We'll wander through cosmic riddles and quantum puzzles, through questions about time and consciousness, all at a pace that hopefully lulls you into the most wonderfully educational slumber. I hope this video isn't too interesting. Though, if it does happen to keep you awake, at least you'll be learning something fascinating about the beautiful mysteries that scientists still can't solve. Not the worst way to spend a sleepless night, pondering the impossible alongside history's greatest thinkers. Before we drift into these unsolved riddles together, I'd love it if you gave this video a like and maybe even subscribed if you haven't already. It really helps this curious little channel grow and means more wondering minds can find their way to these gentle explorations of science's greatest puzzles. I'd also love to know where you're watching from and what time it is for you right now. Are you tuning in from a cozy bed in Stockholm at midnight, watching the winter darkness outside your window? Or perhaps you're listening from a hammock in Brisbane at 3 a.m. in the afternoon, pretending to read but letting these mysteries wash over you instead. Let me know in the comments. It's always such a joy to see this peaceful community scattered gently across the globe, all wondering together. Now, settle in, get comfortable, adjust your pillow, let your shoulders drop away from your ears, allow your breathing to slow just a little. You don't need to remember any of this. You don't need to take notes or stay alert or solve these problems yourself. Goodness knows, scientists with decades of training haven't managed that yet. Just let the words wash over you like soft rain on a quiet evening. And as we begin this gentle voyage into the unknown, remember that this video is for educational and relaxation purposes only. It's not intended as medical advice, a replacement for your physics degree, or a solution to these centuries-old riddles, though it might make your brain feel pleasantly drowsy while contemplating the infinite. Ready? Let's begin. Let's talk about something you've experienced every single moment of your life. Something so fundamental that you probably never think about it at all. The fact that time moves forward. Right now, as you lie there listening, seconds are ticking by. Minutes accumulate. The universe ages. You're getting older, imperceptibly but inevitably, and there's nothing you can do to stop it or reverse it. Time flows in one direction only, from past to future, carrying everything along with it, like leaves floating down a river. But here's the fascinating thing, the thing that has puzzled physicists for over a century. Nothing in the fundamental laws of physics says time has to work this way. When you look at the equations that govern how particles move, how forces interact, how energy flows through the universe, almost all of them work just as well if you run time backward. If you filmed a collision between two billiard balls and played it in reverse, the laws of motion would be perfectly satisfied. The equations don't care which direction time flows. They're what physicists call time symmetric. And yet, you can't unbreak an egg. You can't watch smoke flow back into a candle. You can't watch a tree grow younger or see a wave pull back together after it's crashed on the shore. Time has an arrow, a direction, an undeniable one-wayness that seems to violate the very symmetry written into our deepest physical laws. This is called the arrow of time problem, and it's one of the most quietly profound mysteries in all of science. You might think the answer is obvious. Things fall apart, right? Order becomes disorder. That's just how the universe works. And you wouldn't be wrong exactly. You'd be describing something called entropy, the tendency for systems to move from organized states to disorganized ones. A neat stack of papers becomes scattered, an ice cube melts into water, a sandcastle crumbles. Entropy always increases, or at least that's what the second law of thermodynamics tells us. And maybe, you might think, that's why time has a direction. Entropy points the way forward. But here's where things get curious, where the mystery deepens rather than resolves. Entropy is a statistical concept. It's about probability and large numbers of particles. When you have billions and billions of molecules bouncing around, they're vastly more likely to end up in disordered arrangements than ordered ones, simply because there are so many more ways to be messy than to be neat. It's a bit like shuffling a deck of cards. Sure, you might get them in perfect order, but the odds are astronomically against it. Most of the time, you'll get a random arrangement. That's entropy. And so the universe, filled with countless particles all bouncing and jiggling and moving about, naturally tends toward more probable, more disordered states. The ice cube melts because there are many more ways for water molecules to be scattered through the liquid than trapped in a rigid crystal. The coffee mixes with the cream because there are far more ways for the molecules to be intermingled than separated. Entropy increases not because of some fundamental law saying it must, but because disorder is simply more likely than order. But, and this is the part that kept physicists like Ludwig Boltzmann awake at night in the late 1800s, if entropy is just about probability, then technically, entropy could decrease. It's wildly unlikely, but not impossible. In principle, all those scattered water molecules could randomly arrange themselves back into an ice cube. All the air molecules in your room could randomly drift into one corner, leaving you in a vacuum. The chances are so small as to be essentially zero, but they're not actually zero. The laws of physics don't forbid it. So why do we only ever see entropy increase? Why does time have an arrow if the underlying physics is reversible? This is where the mystery lives, quietly, patiently, waiting for an answer. Some physicists point to the beginning of the universe itself. Perhaps, they suggest, the universe started in an incredibly low entropy state, highly ordered, tightly packed, all the energy and matter compressed into an impossibly small point at the Big Bang. And ever since then, for nearly 14 billion years, the universe has been doing what any system does, moving toward more probable, higher entropy states. The arrow of time, in this view, is just entropy flowing downhill from that special, low entropy beginning. It's an elegant idea. The universe was born organized and has been getting messier ever since, and we call that increasing messiness the passage of time. The future is the direction of higher entropy. The past is the direction we came from, where things were more ordered, simple, right? Not quite. Because now you have to ask, why did the universe start in such a low entropy state? What made the Big Bang so incredibly organized? If high entropy states are more probable, and they are by an enormous margin, then the universe should have started in a messy, disordered state. The fact that it didn't, the fact that it began with such exquisite order, is itself a mystery. It's like shuffling a deck of cards once and getting them in perfect sequence. You'd be justified in wondering if something strange was going on. Some scientists have proposed that our universe is just one region in a vast multiverse, and perhaps different regions have different arrows of time. Maybe somewhere else, in another pocket of reality, time runs backward. Or maybe time doesn't run at all, and everything exists in a timeless quantum superposition. These ideas are fascinating, philosophically rich, and utterly impossible to test with our current technology. Others suggest that time itself might be an illusion, an emergent property that only appears at large scales, like the way temperature only makes sense when you're talking about many particles together. At the level of individual atoms, there's no such thing as temperature, just kinetic energy. Maybe time is like that. Maybe at the deepest level of reality, there's no past or future, no flow, no arrow, just existence, timeless and still. But then you'd have to explain why we experience time so vividly, why we remember the past but not the future, why we feel ourselves aging and moving forward through moments that seem to flow like water. Saying time is an illusion doesn't make it disappear from our experience. We still live in it. We still watch flowers bloom and wilt. We still see stars born and stars die. Whatever time is, it shapes our reality in profound ways. The physicist Carlo Rovelli has written beautifully about this, suggesting that time might be entangled with our own perspective, with the fact that we're macroscopic beings made of countless particles, not fundamental entities outside the universe looking in. From our vantage point, inside the system, thermodynamics matters, entropy matters, and so time has an arrow. But from some other perspective, say a hypothetical observer outside space-time itself, perhaps there is no arrow. Perhaps everything just is, all at once, and we're only seeing one slice of a timeless reality. It's enough to make your head spin, or perhaps in this case, to make it gently rest against your pillow, wondering. The truth is, we don't know. More than a century after Boltzmann's pioneering work on entropy, more than 100 years after Einstein revolutionized our understanding of space-time, we still don't fully understand why time flows the way it does. We can describe it. We can measure it. We can build clocks that track it with astonishing precision. But we can't quite explain it. And maybe that's all right. Maybe some mysteries are meant to remain mysterious, at least for now. Maybe the arrow of time is one of those fundamental features of reality that we'll puzzle over for centuries more, adding layer upon layer of understanding without ever quite reaching the bottom. Or maybe tomorrow, or next year, or in a decade, some brilliant mind will have an insight that cracks it all wide open and will finally understand why time only ever moves forward, why the universe ages, why we can't go home again. For now, though, as you lie there in your particular moment of time, feeling it slip past you second by second, you can take some comfort in knowing that even the greatest minds in physics are still wondering about this alongside you. You're in good company with your confusion. Time remains, for all of us, beautifully and stubbornly mysterious. Let's pause for a moment and let that settle. Time flows. We don't know why, and somehow that makes it even more remarkable. Now we drift into something even stranger, if you can imagine it. Something invisible. Something we can't touch or see or detect directly, yet something that makes up most of the matter in the universe. It sounds like science fiction, doesn't it? An invisible substance pervading all of space, holding galaxies together with its gravity, shaping the structure of the entire cosmos. But this isn't fiction. This is one of the most well-supported and simultaneously most mysterious aspects of modern cosmology. This is dark matter. The story begins, as many good stories do, with someone noticing that something wasn't quite right. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying a collection of galaxies called the Coma Cluster. He was measuring how fast the galaxies were moving, watching them swirl around their common center of gravity like dancers in a cosmic ballet. And when he did the math, something didn't add up. The galaxies were moving too fast. You see, gravity holds clusters of galaxies together, just like it holds the solar system together. The more mass you have, the stronger the gravitational pull, and the faster things can orbit without flying apart. It's a bit like swinging a ball on a string. The faster you swing it, the tighter you have to hold on. Zwicky calculated how much mass the Coma Cluster should have based on all the stars he could see, all the glowing galaxies visible in his telescope. Then he calculated how fast those galaxies should be moving based on that mass, and the numbers didn't match, not even close. The galaxies were moving so fast that they should have flung themselves apart long ago, scattered across the universe like sparks from a fire. Yet there they were, held together, bound by gravity far stronger than the visible matter could account for. Zwicky proposed something radical. There must be matter we can't see, dark matter, providing the extra gravitational pull needed to keep everything together. Most astronomers at the time thought he was being a bit eccentric. They filed his idea away as interesting but unproven, and for decades it remained on the margins of serious science. Then, in the 1970s, an astronomer named Vera Rubin changed everything. She was studying individual galaxies, measuring how fast stars orbit around the galactic center. In our own Milky Way, and in countless other galaxies, stars farther from the center should move more slowly, just like planets farther from the sun move more slowly. Neptune plods along at a leisurely pace compared to Mercury's frantic orbit, That's basic Newtonian physics, the same gravity that governs falling apples and orbiting moons. But that's not what Rubin found. When she measured the rotation speeds of stars in spiral galaxies, she discovered something peculiar. Stars near the edge of galaxies were moving just as fast as stars closer to the center, sometimes even faster. It was as if the galaxies were rotating like solid disks rather than loose collections of stars following their own gravitational trajectories. The rotation curves, as they're called, were flat when they should have been declining. You might think the stars at the edge should just fly off into space, unable to maintain their orbit at such high speeds. And you'd be right. They should, if the only matter in the galaxy were the matter we can see. Stars, gas clouds, planets, all the glowing, luminous stuff that telescopes can detect. But they don't fly off. Something is holding them in place. Something with mass, something with gravity, something utterly invisible. Rubin's work was meticulous and undeniable. Galaxy after galaxy showed the same pattern. The universe was clearly full of matter that didn't emit light, didn't absorb light, didn't interact with electromagnetic radiation in any way we could detect. It was there only by its gravitational influence, tugging on stars and gas, shaping the rotation of galaxies, holding cosmic structures together. The scientific community couldn't ignore it anymore. Dark matter, once a fringe idea, became mainstream. But here's the deeply curious part, the part that keeps physicists awake at night, or in your case, hopefully helps you drift off to sleep. We still don't know what dark matter is. Not really. We know it's there. We can map it by observing how it bends light from distant galaxies, creating gravitational lenses that distort the images of background objects. We can see its influence in the cosmic microwave background, the afterglow of the Big Bang. We can trace its distribution throughout the universe, see how it forms vast filaments and halos, creating the scaffolding on which galaxies form. We know dark matter doesn't emit light. We know it doesn't absorb light. We know it doesn't interact with ordinary matter through any force except gravity. It's not made of atoms as we know them, not protons and neutrons and electrons bound together. It's something else entirely, some exotic particle or particles that make up roughly 85% of all matter in the universe. You, me, Earth, the Sun, every star you've ever seen, every galaxy, every shining nebula. All of that, all the ordinary matter we're familiar with, is just 15% of the matter that exists. We're the minority. We're the strange stuff. Dark matter is the norm. Scientists have proposed many candidates for what dark matter might be. Maybe it's WIMPs, weakly interacting massive particles, theoretical particles that barely interact with ordinary matter but have mass and therefore gravity. Physicists have built incredibly sensitive detectors deep underground, shielded from cosmic rays, waiting to catch a dark matter particle bumping into an ordinary atom. So far, nothing. The detectors sit there, quietly, watching, recording every tiny vibration and temperature fluctuation, and the dark matter, if it's there, passes through undetected, ghost-like. Maybe it's axions, hypothetical particles far lighter than electrons, swarming through space in vast numbers. Or maybe it's primordial black holes, tiny black holes formed in the first moments after the Big Bang, scattered throughout the cosmos. Too small to emit Hawking radiation, but massive enough to exert gravitational influence. Or perhaps it's something we haven't even thought of yet, some particle or phenomenon that exists outside our current theoretical framework, waiting to be discovered. The search continues, gently, persistently. Scientists build bigger detectors, run longer experiments, refine their theories. They collide particles in accelerators like the Large Hadron Collider, hoping to create dark matter particles in the lab, even briefly. They scan the skies for gamma rays that might signal dark matter particles annihilating each other in the hearts of galaxies. They analyze data, write papers, hold conferences, debate possibilities. And still, dark matter remains elusive, invisible not just to our eyes, but to every instrument we've devised. Some physicists have wondered if perhaps we're approaching this all wrong. Maybe there is no dark matter. Maybe instead, our understanding of gravity is incomplete. Newton gave us one description of gravity. Einstein refined it with general relativity, showing that gravity isn't a force, but a curvature of space-time. What if there's another refinement needed? Another layer we haven't uncovered? What if gravity behaves differently at galactic scales than we think? This idea is called modified Newtonian dynamics, or MOND, and it's been around since the 1980s. The basic premise is that gravity might be slightly stronger at large distances than Einstein's equations predict, just enough stronger to keep galaxies rotating the way they do without needing dark matter. It's an elegant idea in some ways. No invisible substance required, just a small tweak to our gravitational equations. But MOND has problems. It works well for explaining galaxy rotation curves, but it struggles to explain other phenomena that dark matter handles beautifully, like the way galaxy clusters bend light, or the patterns we see in the cosmic microwave background. Most physicists still favor dark matter over modified gravity, simply because dark matter fits more of the data. But science remains open to possibilities. Maybe the truth is some combination of both. Dark matter exists, but gravity also behaves a bit differently than we thought. Maybe the universe is more complex than either theory alone suggests. Wouldn't that be fitting? The cosmos, stubbornly resisting our attempts to simplify it, insisting on being rich and layered and strange. Think about this for a moment, as you lie there in the darkness of your room. The darkness around you is familiar. It's just the absence of light, empty space between you and the walls. But the darkness of dark matter is different. It's not empty. It's full, brimming with invisible particles streaming through space, through Earth, through you. Right now, countless dark matter particles are passing through your body, through the atoms that make up your skin and bones, ghosting through without a trace. You're immersed in it, swimming in an invisible ocean you can't feel or see. In a way, we're like fish who've just discovered that water exists. We've spent all of human history experiencing dark matter's effects without knowing it was there. Every galaxy we've ever observed, every structure in the cosmos, has been shaped by dark matter's gravity. It's been there all along, silent and invisible, and we never noticed until we started doing the math. Until we started measuring rotation curves and gravitational lensing, and realized something was missing, or rather, something was present that we couldn't see. It's humbling, isn't it? After centuries of scientific progress, after splitting atoms and mapping the human genome and sending probes to the edge of the solar system, we still don't know what most of the universe is made of. We've catalogued the periodic table, understood the standard model of particle physics, identified every force and particle in ordinary matter, and it turns out that's just 15% of the story. The rest, the vast majority, remains a mystery. But what a beautiful mystery it is. Dark matter reminds us that the universe still has secrets, still has depths we haven't plumbed. It invites us to keep looking, keep wondering, keep building better telescopes and more sensitive detectors. It promises that there are still discoveries waiting, still Nobel Prizes to be won, still moments of revelation ahead when someone, somewhere, will finally detect a dark matter particle or construct a theory that explains it all. Until then, we live in a cosmos where most of what exists is invisible, where the majority of matter reveals itself only through its absence, through the way it shapes visible things while remaining hidden itself. Let that sink in slowly. Most of the universe is invisible, and somehow that feels appropriate. The cosmos, keeping its secrets, the darkness, full of mysteries. Speaking of darkness, we should probably talk about its even stranger cousin. If dark matter is mysterious, dark energy is downright bewildering. But we'll save that for later. Let it wait patiently while we explore other puzzles first. For now, rest in the knowledge that the universe is vast, mostly invisible, and absolutely full of matter we can't see but can't deny. Somewhere in that dark ocean, answers are waiting. We just have to find the right way to look. Let's drift now into the realm of the very small, where things get so strange that even physicists who work with these phenomena every day admit they don't fully understand what's happening. We're entering the quantum world, where particles behave like waves, where things can be in multiple states at once, and where the simple act of looking at something changes what it is. This is the domain of quantum mechanics, and nestled at its heart is one of the most philosophically troubling problems in all of science: the measurement problem. Imagine, if you will, a particle, let's say an electron. In the quantum world, before you measure it, that electron doesn't have a definite position. It's not hiding somewhere, waiting to be found. It's genuinely in multiple places at once, existing in what physicists call a superposition of states. The electron is described by a wave function, a mathematical entity that gives you probabilities for where the electron might be found, but doesn't tell you where it actually is, because where it actually is isn't a question that has an answer yet. This isn't just theoretical speculation. This is what experiments show us, again and again, with such consistency that quantum mechanics has become the most precisely tested theory in all of science. Every piece of technology that uses semiconductors, your phone, your computer, the device you're listening to this on, works because engineers understand and exploit quantum mechanics. The theory works. It makes predictions that come true with astounding accuracy. And yet, what it tells us about reality is so strange that we're still arguing about what it means nearly a century after its mathematical formulation. So there's your electron, spread out in a quantum haze of probability, existing in many places simultaneously. Not in some places more than others. Actually, genuinely, in multiple places at once. The way a wave on the ocean isn't in one spot, but extends across the water's surface. And then you measure it. You set up a detector, you observe, you check where the electron is, and suddenly, instantly, the wave function collapses. The electron is found in one specific location. The superposition vanishes. The many possibilities become one actuality. This is the measurement problem. Why does measurement make the wave function collapse? What counts as a measurement? Where does the probability wave go? And most troubling of all, does the electron really exist in multiple places at once before measurement? Or is the wave function just describing our ignorance of where it really is? You might think the answer is obvious. Of course, the electron is really in one place all along. We just don't know where until we look. The wave function, in this view, is just a mathematical tool describing our uncertainty, like saying there's a 50% chance of rain. It doesn't mean the weather is in a superposition of raining and not raining. It means we don't know which it will do. Similarly, maybe the electron is in one place, and we're just uncertain where until we measure it. This interpretation is called the hidden variables approach, and it's deeply intuitive. Einstein loved it. He never accepted that quantum mechanics was a complete description of reality. God does not play dice, he famously said, expressing his conviction that there must be some deeper level of description where things are definite and determined, even if we can't access that level directly. Perhaps there are hidden variables, hidden properties that determine where the electron really is, properties we just haven't discovered yet. The problem is, experiments have shown that hidden variables don't work, at least not the simple kind Einstein imagined. In the 1960s, a physicist named John Bell devised a mathematical test, now called Bell's theorem, that could distinguish between quantum mechanics as usually understood and a universe with local hidden variables. Experiments have been performed countless times, with increasing sophistication, and the results consistently support standard quantum mechanics. Whatever is happening at the quantum level, it doesn't seem to involve hidden properties that exist independently of measurement. So if the electron doesn't secretly have a position before you measure it, what does it have? The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, says the electron has only the wave function, only probabilities. It doesn't become real, doesn't become actual, until observed. Measurement causes collapse. Before that, the electron is fundamentally indeterminate, genuinely undecided about where it is. The act of observation doesn't reveal a pre-existing reality. It creates reality, selecting one outcome from many possibilities. But this raises uncomfortable questions. What counts as an observation? Does it have to be a human? Does consciousness matter? If a detector records the electron's position, but no one looks at the detector, has the wave function collapsed? What about a cat looking at the detector? A bacterium? An atom? Where's the boundary between the quantum world of superposition and the classical world of definite outcomes? This is where Schrödinger's cat comes in, that famous thought experiment you've probably heard of. Erwin Schrödinger, who helped develop quantum mechanics but was troubled by its implications, imagined a cat in a sealed box with a device that has a 50% chance of killing the cat, triggered by a quantum event, say, a radioactive atom that might or might not decay. Until you open the box and look, quantum mechanics says the atom is in a superposition of decayed and not decayed. And if the cat's fate is tied to the atom, then the cat must also be in a superposition of alive and dead, which is absurd. Cats are not both alive and dead. They're one or the other, definitely, regardless of whether anyone is looking. Schrödinger proposed this thought experiment to show how ridiculous it was to apply quantum rules to everyday objects, but instead of solving the problem, he just highlighted how deep it goes. The cat seems obviously ridiculous, but where do you draw the line? If an electron can be in superposition, why not an atom? If an atom, why not a molecule? If a molecule, why not a virus, a cell, a cat, you? At what point does the quantum world of multiple possibilities give way to the classical world of single actualities? Some physicists say the answer has to do with decoherence, the process by which quantum systems interact with their environment and lose their quantum properties. A single electron in isolation can maintain superposition. But a cat is made of trillions of atoms, all interacting with each other and with air molecules and light and heat. All those interactions cause the quantum information to leak away, to decohere, forcing the system into one definite state. In this view, measurement isn't special. It's just a particularly strong form of interaction. The wave function doesn't collapse because someone observes it. It decoheres because it interacts with a macroscopic environment. This helps explain why we don't see quantum effects in everyday life. Large objects decohere almost instantly, far too fast for us to notice any superposition. But it doesn't fully solve the measurement problem, because decoherence explains why we see one outcome, not which outcome we see. The wave function still describes multiple possibilities even after decoherence. We just can't detect the superposition anymore, but something still has to select which possibility becomes real. Unless, perhaps, all of them do. This is the many worlds interpretation, proposed by Hugh Everett in the 1950s, and often considered the most extravagant solution to the measurement problem. According to many worlds, the wave function never collapses. Ever. All the possibilities described by quantum mechanics are real and actually happen. When you measure an electron's position, the universe splits. In one branch, you find the electron here. In another branch, you find it there. Both versions of you exist in separate, non-interacting realities, each seeing a different outcome. Every quantum measurement creates new branches of reality, an endlessly forking tree of parallel universes where every possibility is realized somewhere. It sounds like science fiction, and perhaps it is. But many physicists take it seriously because it solves the measurement problem without requiring anything special about measurement. The wave function evolves deterministically, just as Schrödinger's equation says it should. There's no collapse, no mysterious transition from possibility to actuality. Everything that can happen does happen, just in different branches of reality. You only see one outcome because you're in one branch, but other versions of you in other branches see different outcomes. The philosophical implications are dizzying. If many worlds is correct, then every decision you've ever made has spawned multiple timelines. In some universe, you took a different job. In another, you live in a different city. In yet another, you never started listening to this video at all. Every quantum event, every particle interaction, branches reality into countless copies, creating a vast multiverse of parallel worlds that can never communicate with each other. It's elegant in its completeness, disturbing in its extravagance, and utterly impossible to test, because by definition, we can't observe the other branches. Or maybe the answer is something else entirely. Maybe consciousness does play a role, as some interpretations suggest. Maybe the universe is more like a participatory system, where observers and observed are entangled in some fundamental way, and reality emerges from their interaction. Maybe time itself is key, and measurement involves a kind of temporal asymmetry we don't fully understand. Maybe quantum mechanics isn't the final theory, and some deeper framework will eventually explain what's really happening. The truth is, we don't know. Nearly a century after the development of quantum mechanics, after countless experiments confirming its predictions, after building technologies that depend on quantum effects, we still don't understand what measurement is or why it has the effects it does. We can calculate, we can predict, we can engineer quantum computers and quantum cryptography systems, but we can't explain what's actually happening when we look at a quantum system and find it in one state rather than another. Different physicists hold different views. Some favor Copenhagen, some prefer many worlds, some think decoherence is the whole story. Some believe hidden variables might work if we make them non-local, allowing instantaneous connections across space. There's no consensus. It's not that we lack data. Quantum mechanics is extraordinarily well tested. It's that the data doesn't tell us which interpretation is correct, or even whether the question of interpretation matters. Some physicists, frankly, don't care. They use the phrase, "shut up and calculate," attributed to Richard Feynman, to express the view that quantum mechanics works. That's what matters. And worrying about what it means is a waste of time. Just use the equations, make your predictions, build your technologies, and move on. The measurement problem, in this view, is a philosophical quibble, not a scientific question. But many others find that unsatisfying. Physics isn't just about making predictions, it's about understanding reality. And if quantum mechanics is telling us something deep about the nature of reality, something about how observation relates to existence, how possibility becomes actuality, how the universe decides what's real, then we should try to understand it, even if it's difficult, even if it challenges our intuitions about how things should work. Lying there in the darkness, you might find something oddly comforting in all this uncertainty. The universe, at its most fundamental level, seems to be genuinely undecided, hovering between possibilities until something, measurement, interaction, consciousness, who knows, makes it choose. There's a softness to that, a lack of rigidity. Reality isn't fixed and determined all the way down. It's fluid, probabilistic, open. The future isn't written in stone, carved out in some deterministic clockwork universe. It's being created moment by moment as quantum possibilities collapse into definite outcomes. Or maybe it's all written, all determined, and we just can't see the mechanism. Or maybe reality is constantly branching, and every version of you experiences a different outcome. Or maybe the question itself is wrong, based on faulty assumptions about what existence means. The measurement problem remains open, gently waiting for someone to finally understand it, or perhaps forever remaining one of those deep puzzles that reminds us how strange the universe truly is. For now, let it rest. The quantum world does its quantum dance. Particles superpose and collapse, measurements yield results, and the mechanism behind it all stays stubbornly mysterious. Perhaps that's fitting. The smallest things in the universe, the fundamental particles that make up everything, following rules we can describe but can't quite comprehend. It's beautiful in a way. Beautiful and bewildering and perfectly suited to making your mind drift gently towards sleep, wondering about electrons and wave functions and the curious boundary between possible and actual. Take a breath. Let it settle. The quantum realm will still be there tomorrow, still strange, still full of unanswered questions. For tonight, just let the mystery wash over you, peaceful and unresolved. Now we turn inward, away from galaxies and particles, away from the external universe, and towards something even more intimate and mysterious, the fact that you're aware. Right now, lying there, you're experiencing something. You can hear these words, or see them, or both. You might feel the weight of your blanket, the softness of your pillow, perhaps a gentle ache somewhere in your body. You might be thinking about what you'll do tomorrow, or remembering something from earlier today. You might be feeling sleepy, or curious, or peaceful, or restless. All of this is happening inside your consciousness, that private inner world where experience occurs. And here's the absolutely fascinating thing, the thing that has puzzled philosophers for centuries and scientists for decades. We have no idea how consciousness happens. None. We don't know why there's something it's like to be you, why your brain doesn't just process information in the dark, mechanically, without any inner light of awareness. We don't know why matter becomes mind, why neurons firing should feel like anything at all. This is called the hard problem of consciousness, and it might be the deepest mystery we've encountered yet. Let's start with what we do know, which is quite a lot actually. We know that consciousness is associated with the brain. When certain parts of your brain are damaged, certain aspects of consciousness change or disappear. Damage to the visual cortex can eliminate visual experience. Damage to language areas can affect the stream of verbal thought. Anesthesia, which affects brain chemistry, can turn consciousness off entirely. You go under, time passes, you wake up, and there's simply nothing in between. No experience, no awareness, just a gap. Your brain was working during that time, keeping you alive, regulating your heartbeat and breathing. But the lights were off. Nobody was home. We also know that consciousness seems to emerge from complex information processing. Simple systems, a thermostat, a calculator, even a single neuron, probably aren't conscious. But as systems become more complex, as they integrate information in sophisticated ways, something happens. At some level of complexity, somewhere in the vast network of 86 billion neurons in your brain, all firing and connecting and forming patterns, consciousness emerges. The question is, how? Why? What's the mechanism that transforms electrical and chemical signals into subjective experience? This is what philosopher David Chalmers calls the hard problem, distinguishing it from the easy problems of consciousness. The easy problems, though they're not actually easy at all, involve explaining the cognitive functions associated with consciousness, how we discriminate stimuli, how we integrate information, how we focus attention, how we control behavior. These are difficult scientific questions, certainly, but they're the kind of questions we know how to approach. We can study brain circuits, track neural activity, build computational models, make progress step by step. The hard problem is different. It asks, why is there subjective experience at all? Why doesn't all this information processing happen in the dark, so to speak? Why is there something it feels like to see red, to taste chocolate, to feel pain? You could imagine a philosophical zombie, a creature that behaves exactly like a conscious human, processes information identically, responds to stimuli appropriately, but has no inner experience, no qualia, no feeling of what it's like. The zombie's brain does all the same things your brain does, but nobody's home. There's no experience or experiencing. It's all mechanism, no consciousness. Now, many philosophers and scientists argue that such zombies are impossible. that consciousness necessarily arises from the right kind of information processing. But the fact that we can even conceive of zombies, that the idea doesn't immediately contradict itself, suggests that consciousness is something additional, something over and above the physical processes we can observe and measure. It's what philosophers call an explanatory gap. There seems to be no way to derive facts about subjective experience from facts about brain activity, no bridge from objective physical processes to subjective felt experience. Imagine trying to explain to someone who's never seen red what red looks like. You could describe the wavelength of red light, around 700 nanometers. You could explain how red light stimulates certain cone cells in the retina, how signals travel along the optic nerve, how specific regions of the visual cortex activate. You could give them all the physical and functional information about seeing red, but none of that would convey what red actually looks like, the subjective redness of red, the quale. No amount of physical description captures the experience itself. This is the explanatory gap. We can describe the physical correlates of consciousness, the neural patterns associated with seeing red, or feeling happy, or thinking about breakfast. We can even, with modern brain imaging, predict with reasonable accuracy what someone is experiencing based on their brain activity. But we can't explain why those neural patterns feel like anything. We can't bridge the gap between third-person objective description and first-person subjective experience. Some scientists and philosophers think the gap is just temporary, a result of our current ignorance. Once we understand the brain well enough, once we have a complete theory of neural information processing, consciousness will be explained, and the hard problem will dissolve. It will turn out that asking why consciousness exists is like asking why water is wet. Wetness is just what happens when you have H2O molecules interacting in certain ways. Similarly, consciousness is just what happens when you have neurons interacting in certain complex patterns. There's nothing extra to explain. Others aren't so sure. Philosopher Thomas Nagel wrote a famous paper called "What is it like to be a bat?", arguing that there's something it's like to be a bat, some subjective experience of echolocating, flying, hanging upside down. But we can never know what that's like. We can study bat brains all we want, map every neural connection, understand every aspect of bat cognition, and we still won't know what it feels like to be a bat. The subjective character of experience, Nagel argued, is irreducible to physical description. It's a fundamental aspect of reality that our objective scientific methods can't capture. This leads to some radical proposals. Perhaps consciousness is fundamental, like mass or charge, a basic feature of the universe that can't be reduced to anything more basic. This view is called panpsychism, and it suggests that some form of experience or proto-experience exists all the way down, even in elementary particles. Not that an electron is sitting there pondering existence, but that it has some minimal subjective aspect, some tiny grain of what its likeness. And when these elementary experiential units combine in the right ways, in sufficiently complex systems, they give rise to rich conscious experiences like ours. It sounds bizarre, frankly. The idea that particles have inner lives, however minimal, seems to violate everything we know about physics. Particles don't need consciousness to behave the way they do. They follow equations, obey laws, interact according to forces. Where would consciousness fit in? What would it do? And yet, panpsychism has its defenders, serious philosophers, and even some scientists who argue that it's no stranger than the alternative. That consciousness somehow emerges from completely non-conscious parts, that experience arises from the experienceless. There's something almost poetic about panpsychism, a kind of ancient wisdom buried in modern philosophical language. The universe is alive with experience, suffused with subjectivity, and we conscious humans are just particularly complex eddies in a cosmic stream of awareness. You and I, the stars, the particles, all participating in the same fundamental nature, all feeling in our own ways. It's a comforting thought, perhaps, even if it's wildly speculative. Or maybe consciousness is computational. Maybe what matters isn't the physical substrate, neurons, silicon chips, whatever, but the patterns of information processing. If you could simulate a brain perfectly on a computer, running all the same algorithms, processing information in all the same ways, would that simulation be conscious? Would there be something it's like to be that computer program? Some functionalists say yes. Consciousness is about function, about what a system does with information, not about what it's made of. If it processes information like a brain, it is, in the relevant sense, a brain, and therefore conscious. But this leads to strange conclusions. If consciousness is just about information processing, then maybe very simple systems could be conscious in limited ways. Maybe even thermostats, with their basic feedback loops, have some glimmer of experience. Or maybe there's a threshold of complexity below which there's no consciousness at all, and above which it suddenly emerges. But where's that threshold? And why would complexity alone create experience? Why wouldn't a very complex, unconscious system be possible? Neuroscientist Giulio Tononi has proposed an interesting theory called integrated information theory, which tries to quantify consciousness. According to this theory, consciousness corresponds to integrated information, information that's more than the sum of its parts, that can't be decomposed into independent pieces. A system is conscious to the extent that it integrates information irreducibly. Your brain integrates vast amounts of information across many regions, creating a unified field of awareness. That's why you're highly conscious. A digital camera, even if it processes lots of information, doesn't integrate it in the same way. Each pixel is independent, so the camera isn't conscious, or is conscious to a vastly lesser degree. Integrated information theory makes testable predictions and provides a mathematical framework, which is rare in consciousness studies. But it also has counterintuitive implications. According to the theory, certain simple networks could be highly conscious if they integrate information in the right way, while certain complex systems might not be. And it still doesn't quite answer the hard problem. Why should integrated information feel like anything? Why should there be subjective experience associated with it? The theory quantifies consciousness, but doesn't explain it. Maybe the problem is that we're thinking about it wrong. Maybe consciousness isn't a thing that needs to be explained, but a perspective, a way of describing certain kinds of systems from the inside rather than the outside. When you describe a brain from the outside, neurons firing, chemicals flowing, that's the third-person objective view. When you describe what it's like to be that brain, seeing, thinking, feeling, that's the first-person subjective view. They're two descriptions of the same thing, not two different things. Consciousness doesn't emerge from brain activity. Consciousness is what brain activity feels like from the inside. This is a form of dual aspect theory, the idea that mind and matter are two aspects of the same underlying reality, like two sides of a coin. Neither reduces to the other. Neither is more fundamental. They're complementary perspectives on a single phenomenon. It's an old idea, going back to philosophers like Spinoza, given new life in modern discussions of consciousness. But even if that's true, we're still left wondering why anything has an inside perspective at all. Why isn't there just the outside, just matter moving according to physical laws? Why did the universe bother creating subjective experience? What purpose does it serve? Some argue consciousness must have evolutionary advantages. It helps us survive, make decisions, navigate complex social environments. But you could imagine evolution creating sophisticated information processing organisms that do all those things without any inner light of awareness. Why add consciousness to the mix? Or maybe consciousness is inevitable, a necessary feature of certain kinds of information processing. Maybe when systems reach a certain level of self-reference, when they model themselves and their environment in sufficiently rich ways, consciousness automatically emerges. Maybe asking why consciousness exists is like asking why circles are round. It's just what happens when you have the right configuration. Consciousness isn't added to physical processes. It's intrinsic to them when they're arranged in certain ways. Lying there, aware of being aware, you're participating in this mystery. You are the mystery. Every thought you think, every sensation you feel, every moment of experience is an instance of the hard problem manifesting itself. Consciousness isn't some abstract philosophical puzzle happening elsewhere. It's happening right now, in you, as you listen or read these words, as you drift towards sleep or remain wakeful, as you experience whatever you're experiencing in this moment. And we don't know how it works. We don't know why you're here, why there's a you at all, why the universe has arranged matter in such a way that some of it can look back at itself and wonder. Your brain weighs about 3 pounds, uses about 20 watts of power, contains roughly 86 billion neurons and 100 trillion synapses. And somehow, in all that electrical and chemical activity, there's an experiencer, a subject, a consciousness, you. Maybe future neuroscience will solve this. Maybe we'll discover some principle, some mechanism, some elegant theory that finally explains how brains generate minds, how matter becomes experience, how the subjective emerges from the objective. Maybe one day, consciousness will seem as understandable as digestion or photosynthesis, just another biological process we've figured out. Or maybe not. Maybe consciousness will remain mysterious forever, a permanent gap in our understanding, a reminder that some aspects of reality resist complete explanation. Maybe we'll learn more and more about the correlates of consciousness, the brain structures involved, the patterns of activity, but never quite bridge the explanatory gap. Maybe the hard problem is truly hard, not just difficult, but fundamentally intractable. For now, in this quiet moment, you can rest in the mystery. You exist. You're aware. And how that's possible, why that's the case, remains one of the great unsolved questions of human inquiry. Perhaps that's all right. Perhaps consciousness, that most intimate of phenomena, deserves to keep some secrets. Perhaps being mysterious is part of what makes it precious, part of what makes your awareness of this moment special and irreducible and yours. Let that thought settle softly. You're conscious. We don't know why. And somehow, that makes the fact that you are all the more remarkable. Let's drift outward now, away from the mysteries of mind and back toward the cosmos, but to perhaps the strangest objects in all of space, black holes. You've probably heard of them. Massive stars that have collapsed under their own gravity, creating regions of space-time so warped that nothing, not even light, can escape. They're cosmic vacuum cleaners, pulling in everything that ventures too close, trapping it forever behind an invisible boundary called the event horizon. Once something crosses that threshold, it's gone. Vanished. Lost to the universe. Or so we thought. Because here's the thing about black holes that has troubled physicists for nearly 50 years. They seem to destroy information. And in physics, information isn't supposed to be destroyed. Ever. It can be scrambled, encrypted, hidden in complex patterns, but never truly lost. This principle, called unitarity, is fundamental to quantum mechanics. It says that if you know the complete state of a system at one time, you can in principle calculate its state at any other time, forward or backward. Information is preserved. The universe doesn't forget. But black holes appear to violate this rule. When something falls into a black hole, all the detailed information about that object, what it was made of, how its particles were arranged, every quantum detail, seems to disappear forever. From the outside, you can't tell what went in. The black hole is characterized by just 3 properties: mass, charge, and angular momentum. Everything else is erased. A black hole that formed from a collapsed star looks identical to one that formed from compressed cosmic dust, as long as those 3 properties match. All the complexity, all the information, gone. This is sometimes called the no-hair theorem. Black holes have no hair, no distinguishing features beyond those 3 numbers. It's a deliberately whimsical name for a rather disturbing result. If information truly vanishes into black holes, if the universe can forget, then quantum mechanics as we understand it is incomplete or wrong. And quantum mechanics is our most successful physical theory, tested to extraordinary precision in countless experiments. So which is it? Do black holes break quantum mechanics? Or are we misunderstanding something fundamental about how black holes work? The story begins with Stephen Hawking, who in the 1970s discovered something remarkable. Black holes, despite their name, aren't completely black. They emit radiation. It's called Hawking radiation, and it comes from a fascinating quantum effect near the event horizon. In the quantum vacuum of space, particle-antiparticle pairs constantly pop into existence, borrowing energy from the vacuum for brief moments before annihilating each other. Usually this happens and unhappens so quickly that it has no lasting effect. But near a black hole's event horizon, something different can occur. Imagine a particle-antiparticle pair appearing right at the edge of the horizon. One particle falls in, crossing the event horizon and becoming trapped. The other particle escapes, flying off into space. To a distant observer, it looks like the black hole just emitted a particle. The black hole has radiated. And because energy is conserved, that radiated particle must carry away some of the black hole's mass. Remember, mass and energy are equivalent, EMC2. So the black hole loses mass. It shrinks. Over unimaginably long timescales, a black hole will evaporate completely, radiating away all its mass until nothing remains. This was shocking enough. Black holes aren't eternal after all. They're slowly dying, leaking energy into space in the form of Hawking radiation. But the deeper shock came when physicists asked, what happens to the information? If a black hole eventually evaporates completely, where does the information about everything that fell in go? Does it somehow escape in the Hawking radiation? Or is it destroyed when the black hole vanishes? Hawking initially argued that the information is lost. The radiation, he calculated, is completely thermal, random, featureless, carrying no information about what went into the black hole. It's like burning a book and trying to reconstruct the text from the heat and smoke. The information is gone. But this contradicted quantum mechanics. It created a paradox. Either information is destroyed, violating unitarity, or something is wrong with our understanding of black holes, quantum mechanics, or both. For decades, physicists debated this. Some sided with Hawking, arguing that perhaps information can be destroyed in quantum gravity, that the usual rules break down in such extreme conditions. Others insisted that information must be preserved somehow, that we were missing something crucial about how black holes work. The debate became heated at times, with significant bets placed and strong opinions held. It wasn't just an academic quibble. It touched on fundamental questions about the nature of reality, about whether the universe is deterministic or fundamentally random, about whether physics as we know it holds up in the most extreme environments. Then came a series of insights from string theory and quantum gravity that suggested maybe, just maybe, information isn't lost after all. Maybe it escapes, but in such a scrambled form that we can't easily detect it. Imagine throwing an encyclopedia into a shredder, then burning the shredded pieces, then analyzing the smoke and ash with extraordinary precision. In principle, if you had perfect information about every particle in the smoke, every photon of light, every quantum detail, you could reconstruct the encyclopedia. It would be fantastically difficult, perhaps practically impossible, but not forbidden by the laws of physics. Maybe black holes are like that, perfect scramblers that preserve information but hide it incredibly well. This idea gains support from the holographic principle, one of the strangest ideas in modern physics. The holographic principle suggests that all the information contained in a volume of space can be encoded on the boundary of that space, like a hologram, encoding a 3D image on a 2D surface. Applied to black holes, this means that all the information about everything that fell in is somehow encoded on the event horizon itself, on that two-dimensional surface. When the black hole evaporates, that information gradually leaks out in the Hawking radiation, preserved but scrambled beyond recognition. It's a beautiful idea, almost mystical in its implications. Reality might be fundamentally two-dimensional, with the three dimensions we experience emerging from information encoded on distant boundaries. Your entire life, every thought and experience, could in principle be encoded on some distant surface. The universe might be a hologram, and we're patterns of information dancing on its boundary. It's dizzying to contemplate, especially as you lie there in the three-dimensional space of your room, feeling very much like a three-dimensional being. Hawking himself eventually conceded that information is probably preserved, though he never seemed entirely happy about it. In 2004, he famously admitted he'd been wrong and paid off a bet he'd made decades earlier. But even with this concession, the details remain murky. How exactly does information escape? Where is it encoded during the black hole's lifetime? How does it get transferred to the outgoing Hawking radiation? These questions remain hotly debated. Recent ideas involve something called black hole complementarity, which suggests that information both falls into the black hole and escapes in the radiation, depending on your perspective. To someone falling into the black hole, the information crosses the horizon smoothly and falls toward the singularity at the center. To someone far away, the information never quite crosses the horizon, but gets scrambled and eventually re-emitted in the Hawking radiation. Both perspectives are correct in their own reference frames, complementary descriptions of the same reality, like the wave-particle duality in quantum mechanics. But this leads to its own puzzles. If information is scrambled at the horizon and re-emitted, what happens to the smooth geometry that general relativity predicts? If falling into a black hole isn't a smooth experience, but instead involves hitting a firewall of intense radiation at the horizon, that contradicts relativity's prediction that nothing special happens at the horizon. You should fall through smoothly, not even noticing when you cross until it's too late to escape. This is called the firewall paradox, and it's created a new round of debates about what really happens at black hole horizons. Some physicists propose that the event horizon is actually fuzzy, not a sharp boundary, but a quantum region with complex structure, sometimes called a fuzzball. Others suggest that black holes might have microscopic hair after all, subtle quantum features that carry information. Still others think the problem requires a complete rethinking of how space and time work, that maybe space-time itself is emergent, arising from more fundamental quantum information, and black holes are places where this emergence becomes apparent. There's also the question of what happens at the singularity, the point at the center of the black hole, where curvature becomes infinite and our equations break down. General relativity predicts a singularity, but most physicists believe this is a sign that general relativity is incomplete, that quantum gravity will smooth out the singularity into something more benign. But we don't have a complete theory of quantum gravity yet, so we can't say for sure what's really at the center of a black hole. Maybe it's a tiny region of incredibly dense matter. Maybe it's a gateway to another universe. Maybe it's something we don't have concepts or words for yet. What we do know is that black holes are laboratories for extreme physics, places where gravity is so strong and space-time so warped that quantum effects can't be ignored. They force us to confront the fact that general relativity and quantum mechanics, our two most successful theories, don't quite fit together. In most situations, you can use one or the other. Relativity for large, massive things, quantum mechanics for small, light things. But black holes are both massive and small, both warped space-time and quantum systems. They demand a unified theory, a quantum theory of gravity, which we don't yet have. String theory is one attempt at such a theory, suggesting that particles are actually tiny vibrating strings, and that space-time has extra dimensions curled up at microscopic scales. Loop quantum gravity is another approach, proposing that space itself is quantized, made of discrete chunks like atoms of space. Both frameworks offer insights into black holes and information preservation, but neither is complete or fully tested. We're still groping toward a final theory. guided by paradoxes like the information problem. Lying there in your room, you're separated from the nearest black hole by thousands of light years, safely distant from these cosmic puzzles. But in a sense, the information paradox touches everything. If information can be destroyed, if the universe can truly forget, then the past isn't uniquely connected to the present. Causality becomes fuzzy. The story of how we got here might be fundamentally ambiguous. But if information is preserved, if the universe remembers everything in exquisite detail, then your entire history, every moment you've lived, every thought you've had, is encoded somewhere in the quantum state of the cosmos, never to be lost, always part of the great unfolding pattern. Black holes keep their secrets well. They trap light, warp time, scramble information beyond recognition. They sit at the intersection of our deepest theories, quietly pointing out the places where those theories clash, where our understanding breaks down. Solving the information paradox might require not just better equations, but new ways of thinking about space, time, information, and reality itself. It might require concepts we haven't invented yet, insights that will seem obvious in retrospect, but remain stubbornly hidden for now. Until then, we can marvel at these strange objects, these punctures in space-time, where the universe becomes almost incomprehensibly weird. We can appreciate the paradoxes they create, the questions they raise, the mysteries they embody. And we can recognize that even our most brilliant theories, our most elegant equations, still have gaps, still leave room for wonder and uncertainty, and the slow, patient work of science trying to understand. Let that sink in gently. Black holes, the universe's great erasers and encryptors. Information, potentially lost or perfectly preserved. Physics, still incomplete, still reaching for a final theory. And you, here, now, part of the same universe that creates these cosmic enigmas, thinking about them from a safe distance, letting the mysteries wash over you like gentle waves. Take a breath. The black holes can wait. They're not going anywhere fast. Even their evaporation takes longer than the current age of the universe. For tonight, just know they're out there, holding secrets, preserving or destroying information. We're not quite sure which. Beautiful, terrifying, and perfectly mysterious. Now we turn to what might be the most embarrassing problem in all of physics. A prediction that's wrong by such an enormous factor that it makes scientists wince. We're talking about dark energy, or more precisely, the cosmological constant, and the fact that when physicists try to calculate its value from first principles, they get an answer that's off by a factor of 10 or 120. That's not a typo. Not 120, but 10 to the power of 120. A 1 followed by 120 zeros. It's arguably the worst prediction in the history of science, and yet somehow, we live in a universe where this catastrophically wrong calculation still leads to something that exists and matters deeply. Let's start with what dark energy is, or rather, what it does, because what it is remains profoundly mysterious. In the late 1990s, two teams of astronomers were studying distant supernovae, exploding stars that serve as cosmic lighthouses, allowing us to measure distances across the universe. They expected to find that the expansion of the universe was slowing down. After all, gravity pulls everything together, so the universe's expansion, which began with the Big Bang, should be gradually decelerating, like a ball thrown upwards slowing as gravity pulls it back. But that's not what they found. Instead, they discovered that the expansion of the universe is accelerating, getting faster. Galaxies are rushing away from each other at an increasing rate, as if some invisible force is pushing them apart. This was so unexpected, so contrary to what everyone thought was happening, that the teams checked and rechecked their data, looked for errors, tried to find alternative explanations. But the result held. The universe isn't just expanding, it's accelerating its expansion. Something is working against gravity, some kind of anti-gravity effect, and we call it dark energy. The simplest explanation for dark energy is that it's the energy of empty space itself, what physicists call the vacuum energy or the cosmological constant. Quantum mechanics tells us that even perfectly empty space isn't truly empty. It's filled with quantum fields, and those fields have a lowest energy state, a ground state, but that ground state isn't zero. There's residual energy just from the fields existing, energy inherent in the fabric of space-time itself. And energy, according to Einstein's general relativity, curves space-time. Vacuum energy should act like a kind of pressure, pushing space apart, causing the expansion of the universe to accelerate. So far, this sounds reasonable. Empty space has energy. That energy affects gravity, and we observe the effects in the accelerating expansion of the universe. The problem comes when you try to calculate how much vacuum energy there should be. When physicists add up all the contributions from all the quantum fields we know about, they get a number, a very large number, absurdly large, about 1,120 times larger than what we observe. To put this in perspective, imagine you're trying to measure the width of the United States. You do your calculation and predict it should be 10,120 meters wide. That's not just wrong. It's wrong by a factor that would make the United States vastly, incomprehensibly larger than the entire observable universe. In fact, 10,120 meters is so absurdly large that it dwarfs even cosmic scales. The observable universe is only about 1026 meters across. Your prediction would be off by about 94 orders of magnitude. That's the scale of the cosmological constant problem. Our prediction is so wrong it's almost funny, except it's deeply troubling. If the vacuum energy were actually as large as quantum field theory predicts, the universe would have blown apart almost immediately after the Big Bang, expanding so rapidly that atoms, let alone stars and galaxies and planets and people, could never have formed. The fact that we exist, that structure exists, that the universe has had time to evolve and cool and create complexity, means the cosmological constant must be much, much smaller than we calculate. In fact, it's not zero. We observe its effects in the accelerating expansion. But it's tiny compared to what theory predicts. Almost zero, but not quite. This is sometimes called the worst fine-tuning problem in physics. Fine-tuning refers to situations where a parameter needs to have a very specific value for things to work out the way they do. A little too large or too small, and reality would be completely different. The cosmological constant appears to be fine-tuned to an extraordinary degree, 120 decimal places of precision. It's as if nature dialed in this value with incredible care, balancing competing contributions to get a number that's almost, but not quite, zero. Why? Why should the vacuum energy be so small? There's no known reason, no principle that requires it. In fact, various contributions to the vacuum energy should be positive and negative, from different quantum fields, and somehow they almost perfectly cancel out, leaving only a tiny residual value. It's like having 100 different bank accounts, some with deposits and some with withdrawals, and discovering that they balance to within a penny when each account contains trillions of dollars. The cancellation seems too precise to be random. Some physicists have proposed that perhaps there's a symmetry we don't know about, some fundamental principle that forces the vacuum energy to be small or zero. Maybe there's a mechanism, like supersymmetry, that naturally creates cancellations between different contributions. Supersymmetry is a proposed extension of the standard model of particle physics that pairs every particle with a superpartner, and these partners would contribute vacuum energy with opposite signs, potentially cancelling each other out. It's an elegant idea, but so far, experiments at the Large Hadron Collider haven't found any evidence for supersymmetric particles. If they exist, they're heavier and more elusive than we hoped. Others suggest that maybe the cosmological constant isn't constant at all. Maybe it's a dynamical field, something that changes over time or varies in space, and what we're observing is just its current value in our region of the universe. This field, sometimes called quintessence, would be yet another component of the cosmos, distinct from matter and radiation, and even from the static vacuum energy. It would be a new kind of entity, slowly rolling down some potential energy landscape, affecting the expansion rate as it goes. But we have no direct evidence for quintessence, and it adds complexity without necessarily solving the fine-tuning problem. Why is this field's energy so small right now? Then there's the anthropic principle, an idea that makes some physicists deeply uncomfortable. The anthropic principle suggests that the cosmological constant has the value it does because if it were much different, we wouldn't be here to observe it. If the vacuum energy were too large, the universe would have expanded too quickly for galaxies to form. If it were negative and too large, the universe would have collapsed back on itself before stars could ignite. The range of values compatible with the existence of complex structures like galaxies, stars, planets, and life is actually quite narrow. So maybe we observe a small cosmological constant not because it's fundamentally likely, but because we're in a universe where it happens to have a life-permitting value. This idea becomes more plausible if you believe in the multiverse, the notion that our universe is just one of countless universes, each with different values for fundamental parameters. In this vast ensemble of universes, most would have cosmological constants that are inhospitable to life. But in some tiny fraction, the value would be just right. And naturally, we find ourselves in one of those rare universes, not because it's special in any cosmic sense, but because that's the only kind of universe where observers like us can exist to wonder about these things. It's a selection effect, not a fundamental explanation. The anthropic principle is philosophically divisive. Some see it as a cop-out, a way of giving up on finding deeper explanations. If you can explain any observation by saying, it has to be this way, or we wouldn't exist, then you're not really explaining anything. You're just noting a correlation between our existence and certain parameter values. Others see it as a profound insight about the nature of science and observation, a recognition that some questions might not have answers beyond, this is the way things are in the universe we happen to inhabit. Lying there, you might wonder what it means that the universe seems fine-tuned for your existence. Is it meaningful? Is it evidence of design, or a multiverse, or just a brute fact we have to accept? The cosmological constant whispers these questions softly, not providing answers but highlighting how little we understand about why the universe has the properties it does. There's also the possibility that we're simply wrong about how to calculate vacuum energy. Quantum field theory, for all its successes, is a theory that works in flat spacetime, not curved spacetime. General relativity tells us spacetime is curved by matter and energy, but quantum field theory mostly ignores this curvature. When we calculate vacuum energy, we're using a framework that might not be appropriate for the question. Maybe a true theory of quantum gravity, something that unifies quantum mechanics and general relativity, would give a different answer, one that naturally produces a small cosmological constant without fine-tuning. String theory, that ambitious attempt to describe all forces and particles as vibrations of tiny strings, offers some hints in this direction. In string theory, the cosmological constant depends on the shape of extra dimensions and the configuration of various fields, and there might be mechanisms that stabilize it at a small value. But string theory itself is incomplete and untested, a beautiful mathematical structure that hasn't yet made contact with experimental reality. It's a promising avenue, but not a solution we can claim with confidence. Another possibility is that we're measuring the wrong thing, that dark energy isn't vacuum energy at all, but something else we've confused for it. Maybe general relativity breaks down at cosmological scales, and what looks like accelerating expansion is actually a sign that gravity works differently than we think over vast distances. Several modified gravity theories have been proposed, adjustments to Einstein's equations that mimic the effects of dark energy without requiring vacuum energy. But these theories face their own challenges, and most physicists still favor the cosmological constant as the simplest explanation, even if it's profoundly mysterious. What makes this problem particularly frustrating is that we can't just set the cosmological constant to zero and move on. We measure its effects. The supernovae data, the cosmic microwave background radiation, the large-scale structure of the universe, all of these observations point to the same conclusion. There's dark energy. It's about 68% of the total energy density of the universe, and it's causing expansion to accelerate. We can't ignore it. We can only puzzle over why its value is what it is, so small compared to theory, yet large enough to dominate the universe's dynamics. The universe, it seems, is mostly made of things we don't understand. Dark matter, which we discussed earlier, makes up about 27% of the energy density. Dark energy is another 68%. Ordinary matter, stars, planets, gas, dust, everything made of atoms, everything you can see and touch, is only about 5%. We're a small minority in a cosmos dominated by mysterious components. It's humbling, almost amusing. We named ourselves Homo sapiens, wise humans, and yet we don't know what most of the universe is made of. But perhaps there's something peaceful in that ignorance. The universe doesn't owe us explanations. It simply is, unfolding according to its own nature, and we're here briefly, asking questions, making observations, building theories, getting predictions wrong by 120 orders of magnitude, and then trying to figure out why. It's a testament to human persistence, really, that we don't give up in the face of such enormous discrepancies. We keep looking, keep calculating, keep hoping that someday we'll understand why the cosmological constant has the value it does, why the universe expands the way it does, why we live in this particular cosmic configuration and not some other. For now, as you lie there in your room, dark energy is gently pushing the universe apart, stretching space itself, causing galaxies to recede from each other at ever-increasing speeds. In billions of years, if dark energy continues to dominate, galaxies beyond our local group will drift so far away that their light will never reach us. Future civilizations, if they exist, will look up at a darker sky, unable to see the vast cosmic web we observe today. They'll have to take our word for it, that the universe was once filled with galaxies, that expansion is accelerating, that dark energy exists. Or perhaps they'll figure it out from other clues, more clever than we can imagine. But that's far in the future. For tonight, you can rest knowing that the universe is expanding, accelerating, driven by something we call dark energy, but don't really understand. The cosmological constant keeps its secrets fine-tuned to an absurd degree, allowing structure and complexity and life to exist. And physicists keep working on the problem, hoping that one day the numbers will make sense, the fine-tuning will have an explanation, and the universe's expansion will seem less mysterious and more inevitable. Until then, we live with the paradox. Theory predicts one thing, reality shows another, and the gap between them is so vast, it defies comprehension. It's the universe's way of reminding us that for all our knowledge, all our equations and experiments and instruments, we're still just beginning to understand, still learning, still wondering why things are the way they are. Let it rest. The cosmological constant can wait. The universe expands whether we understand it or not, patient and vast and utterly unconcerned with our confusion. And somehow, that's oddly comforting. Let's turn now to something closer to home, something that touches on your own existence in the most direct way possible, the question of how life began. You're alive. Every cell in your body is a tiny, bustling city of molecules, all working together with extraordinary precision. Your DNA contains instructions written in a 4-letter chemical alphabet, instructions that were copied from your parents, who copied them from their parents, stretching back through an unbroken chain of living things for billions of years. But somewhere, sometime, that chain had a beginning. Somewhere in Earth's ancient past, non-living chemistry became living biology. And we don't really know how. This is one of the deepest mysteries in science, perhaps more personal than questions about dark matter or quantum mechanics, because it's about us, about how we came to be. How did lifeless molecules organize themselves into something that could grow, reproduce, evolve, and eventually become conscious? How did chemistry become biology? When did mere matter start doing the extraordinary things that living things do? We know roughly when this happened. Earth formed about 4.5 billion years ago, and for the first few 100 million years, it was a hellish place. Molten rock, volcanic eruptions, asteroid bombardments, an atmosphere of toxic gases. But the planet cooled, oceans formed, and by about 3.8 billion years ago, maybe earlier, there's evidence of life. Simple, single-celled organisms, nothing fancy, but definitely alive. They metabolized, they reproduced, they left chemical traces in ancient rocks that we can still detect today. So, life emerged surprisingly quickly, within the first billion years of Earth's history, possibly within the first few 100 million years after the planet became habitable. But how? That's the question that has puzzled scientists for over a century. The problem is that life, even the simplest single-celled life we know of, is extraordinarily complex. A bacterium contains thousands of different proteins, each folded into a precise three-dimensional shape, each catalyzing specific chemical reactions. It has a membrane that separates inside from outside, channels that let certain molecules through while keeping others out. It has DNA that stores genetic information and machinery that reads that DNA and builds proteins based on its instructions. It has metabolic pathways that extract energy from nutrients and use that energy to power cellular processes. It's an intricate, integrated system, and all the parts need to work together for the cell to function. So you can't just have DNA appear by chance. DNA is useless without proteins to read it and copy it. But proteins can't be made without the information stored in DNA. It's a chicken and egg problem, a closed loop where each component depends on the others. How do you get such an interdependent system started from scratch? How do you go from a pool of simple chemicals to a functioning cell? The classic answer, proposed in the 1920s by scientists like Alexander Oparin and J.B.S. Haldane, is that life began in a primordial soup, a warm ocean or pond, rich in organic molecules, energized by lightning or ultraviolet radiation, where increasingly complex molecules could form over millions of years. In 1953, Stanley Miller and Harold Urey famously tested this idea by simulating early Earth conditions in a flask. They mixed water, methane, ammonia, and hydrogen, then zapped the mixture with electrical sparks to simulate lightning. After a week, they found amino acids, the building blocks of proteins, forming spontaneously. It was remarkable. The ingredients of life could arise from non-living chemistry. But amino acids are just building blocks. You still need to string them together into proteins, and not just any proteins, but functional ones that fold correctly and do useful things. And you need information storage, some way to pass on molecular arrangements to the next generation. You need metabolism, chemical reactions that extract and use energy. You need compartmentalization, a boundary that defines what's inside the organism and what's outside. Getting all of these features to emerge together from a chemical soup seems extraordinarily unlikely. Some scientists have proposed that RNA, not DNA, was the first genetic material. RNA can do something DNA can't. It can act as both information storage and catalyst. Some RNA molecules, called ribozymes, can speed up chemical reactions, including reactions that copy RNA itself. This suggests a possible solution to the chicken and egg problem. Maybe there was an RNA world before DNA and proteins, a time when life was based entirely on RNA. RNA molecules would store information and also perform catalytic functions, and only later did DNA take over information storage and proteins take over catalysis, because they do those jobs more efficiently. It's an elegant idea, and there's some evidence for it. Ribosomes, the cellular machines that build proteins, use RNA as their catalytic core, a molecular fossil, perhaps, from the RNA world. But even the RNA world hypothesis has problems. RNA is difficult to synthesize under plausible prebiotic conditions. It's chemically unstable, breaking down quickly in water. And even if you could get RNA to form, you'd need it to spontaneously organize into sequences that could replicate themselves, which seems statistically unlikely. Random RNA sequences mostly don't do anything interesting. Finding one that can catalyze its own replication is like finding a needle in a molecular haystack. Perhaps life didn't start in a warm pond, but in a more structured environment. Hydrothermal vents, cracks in the ocean floor where hot, mineral-rich water spews out into cold seawater, have become a popular candidate for life's birthplace. These vents create natural chemical gradients, differences in temperature, pH, and concentration, that could drive the formation of complex molecules. The minerals in vent walls could act as catalysts, helping reactions along. And the tiny pores in the rock could serve as natural compartments, protocells where chemical evolution could occur in a protected environment before membranes evolved. There's something appealing about this image. Life beginning in the dark depths of the ocean, in the warmth of volcanic vents, far from sunlight, drawing energy from Earth's interior rather than from the sky. It suggests life might arise wherever there's liquid water and a source of chemical energy, which has implications for the search for life elsewhere. If life can start in such environments, then maybe it's not rare. Maybe every planet or moon with subsurface oceans and hydrothermal activity has a chance of developing life. Maybe we're not alone. But even the hydrothermal vent hypothesis doesn't fully solve the origin problem. You still need to explain how you get from simple organic molecules to self-replicating systems. Some scientists think we're missing a crucial conceptual piece, that we're thinking about life's origin in the wrong way. Maybe life didn't start with replication. Maybe it started with metabolism, chemical cycles that could sustain themselves and gradually became more complex. Or maybe it started with compartmentalization, lipid membranes forming spontaneously and trapping chemicals inside, creating distinct chemical environments where evolution could take hold. There's also the question of whether life on Earth is the only kind of life possible. All life we know uses DNA or RNA for information storage, proteins for catalysis and structure, and a specific set of amino acids and nucleotides. We all share the same genetic code, with minor variations. This suggests we all descended from a common ancestor, that life arose once on Earth and then diversified. But is this the only way life could work? Could there be life based on different chemistry, silicon instead of carbon, ammonia instead of water, entirely different information storage molecules? We don't know, because we only have one example. Life on Earth is incredibly diverse. Bacteria, archaea, fungi, plants, animals, countless forms adapted to nearly every environment on the planet. But at the chemical level, it's all fundamentally the same. We're all using the same toolkit, the same basic machinery. This is sometimes called the N=1 problem in astrobiology. It's hard to draw general conclusions about life when you only have one instance of it. It's like trying to understand what music is based on a single song. Perhaps the chemical basis of life is universal, constrained by the laws of physics and chemistry. Carbon is uniquely good at forming complex molecules because it can make 4 bonds and create long chains and rings. Water is an excellent solvent with unusual properties that make it ideal for biochemistry. Maybe any life, anywhere in the universe, would be carbon-based and water-dependent, using similar chemistry to what we see on Earth. Or maybe life is more flexible than we imagine, and we just lack the imagination to envision alternatives. There's also the unsettling possibility that life's origin was such an unlikely event that it's only happened once in the observable universe. Maybe the steps required to go from chemistry to biology are so improbable that even given billions of years and trillions of planets, it rarely or never happens. We could be a statistical fluke, a one-in-a-universe accident, and that's why we haven't detected any other life despite decades of searching. It's a lonely thought, but not an impossible one. On the other hand, life appeared on Earth remarkably quickly after the planet became habitable. If it takes billions of years for the right conditions and the right chemistry to align, we'd expect life to emerge late in Earth's history, or maybe not at all before the sun expands and destroys the planet. But instead, life showed up early, almost as soon as it possibly could. This suggests that maybe life's origin isn't that improbable. Maybe given the right conditions, liquid water, organic molecules, an energy source, life tends to emerge relatively easily. Maybe the universe is teeming with simple life, and we just haven't looked in the right places or in the right ways. Lying there, you might reflect on the fact that you're part of an unbroken chain of life stretching back nearly 4 billion years. Every organism that contributed to your ancestry successfully reproduced, generation after generation, through ice ages and asteroid impacts and mass extinctions and everything else Earth has thrown at life. The odds of your particular existence are astronomically small, and yet here you are, the product of countless successful reproductions, each one passing along genetic information with small variations, gradually building complexity over deep time. And it all started with some chemical reaction, some self-organizing process in ancient water, some moment when molecules began to replicate and metabolize and become something we'd recognize as alive. We don't know the details. We have hypotheses, experiments, educated guesses, but no definitive answer. The origin of life remains one of science's greatest unsolved problems, a gap in our understanding of how we got here. Some people find this troubling. If we don't know how life began, how can we be sure it began naturally? Maybe it required something more, some spark beyond chemistry, some guiding intelligence. But most scientists resist this conclusion, not because they're philosophically opposed to it, but because there's no evidence for it and no need for it. Chemistry is capable of extraordinary self-organization. Snowflakes form intricate patterns without any blueprint. Crystals grow in beautiful symmetries. Sand dunes organize themselves into ripples and waves. The universe is full of examples of order emerging from disorder through natural processes. Life is more complex than a snowflake, certainly, but it's not obviously different in kind. It's chemistry, perhaps very special chemistry, but chemistry nonetheless. And chemistry, given time and the right conditions, does remarkable things. The question isn't whether chemistry can produce life, but how it did so. What sequence of steps led from simple molecules to self-replicating systems, to cellular life, to the extraordinary diversity we see today? And that question remains tantalizingly open, waiting for some insight, some experiment, some discovery that will finally illuminate those first crucial steps. Maybe we'll never know for certain. The events that led to life's origin happened billions of years ago, and they probably didn't leave much trace. There are no fossils of protocells, no preserved records of the RNA world, no snapshots of primordial metabolism. We have to work backward from modern life, comparing genomes, studying biochemistry, simulating possible prebiotic conditions in labs, hoping to catch glimpses of how it might have happened. It's detective work with most of the evidence lost to time. But the search continues, gently, persistently. Scientists mix chemicals in flasks, bombard them with radiation, measure what forms. They explore hydrothermal vents, looking for clues about what chemistry is possible in those extreme environments. They study extremophiles, organisms that thrive in conditions we'd consider lethal, to understand the boundaries of what life can tolerate. They build computer models, simulating chemical evolution, watching virtual molecules interact and compete, and occasionally stumble onto self-replication. And maybe one day, someone will create life in a lab from scratch, starting with non-living chemicals and watching them organize into something that metabolizes and reproduces. Or maybe we'll find life elsewhere, on Mars, in the oceans of Europa or Enceladus, on an exoplanet around another star, and we'll learn that life's origin is easier or harder or stranger than we imagined. Or maybe the mystery will remain, and we'll live with not knowing, accepting that some questions about our origins may be forever beyond our reach. For now, you can rest in the knowledge that you're alive, that the chemistry in your cells is doing its ancient dance, that you're part of something that started long ago in ways we don't fully understand. You're made of molecules that were once scattered in stellar dust, gathered by gravity into a planet, organized by unknown processes into something that could grow and change and eventually wonder about its own existence. That's remarkable, whether or not we know exactly how it happened. Let that thought settle softly. Life emerged. We're here. And the details of how, while fascinating, don't change the fact that chemistry found a way to become biology, and biology eventually became you, lying there, contemplating the mystery of your own origins. It's beautiful, it's profound, and it's enough, even without all the answers. We return now to the quantum realm, but this time to explore what Einstein famously called spooky action at a distance, a phenomenon so strange that even the physicists who discovered it couldn't quite believe it was real. We're talking about quantum entanglement, a connection between particles that seems to transcend space and time, linking objects across any distance instantaneously in ways that challenge our deepest intuitions about how reality works. Imagine two particles, let's say two electrons, that interact and then separate, flying off in opposite directions. In the quantum world, before you measure them, each electron exists in a superposition of states. An electron has a property called spin, which can be either up or down, and before measurement, the electron's spin is genuinely undecided, existing in both states at once. That's the superposition we talked about earlier. But here's where it gets strange. When two particles become entangled, their quantum states become correlated in such a way that measuring one particle instantly affects the other, no matter how far apart they are. So, you measure the first electron and find its spin is up. At that exact moment, the second electron's spin becomes down, even if it's on the other side of the galaxy. The particles aren't sending signals to each other. That would violate the speed of light limit. They're not connected by any physical thread or field that we can detect. Yet somehow, they're linked. Measuring one determines the state of the other, instantly, regardless of the distance between them. It's as if the particles share a single quantum state spread across space, as if they're not truly separate, but remain parts of a unified whole. Einstein hated this idea. He, along with physicists Boris Podolsky and Nathan Rosen, wrote a famous paper in 1935 arguing that quantum mechanics must be incomplete. Their argument, now known as the Fermi Paradox, after their initials, went something like this. If measuring one particle instantly determines the state of another particle far away, then either information is traveling faster than light, which violates relativity, or the particles had definite states all along, and quantum mechanics is just describing our ignorance of those states. Since faster-than-light signaling seemed impossible, they concluded that quantum mechanics was missing something, those hidden variables we mentioned earlier. For decades, this remained a philosophical debate. Entanglement was predicted by the equations, but it seemed so weird that many physicists suspected there might be a more reasonable explanation lurking beneath the quantum formalism. Then, in the 1960s, John Bell devised his theorem, providing a way to test whether hidden variables could explain quantum correlations. Experiments were performed, refined, repeated with increasing precision. And the answer came back, again and again. Nature really does exhibit quantum entanglement. The correlations between entangled particles are stronger than any local hidden variable theory could produce. The universe is genuinely non-local in this specific quantum way. This doesn't mean you can send information faster than light using entanglement. You can't. The results of measuring one entangled particle look completely random until you compare them with the measurements of the other particle. Only when you bring the two sets of results together, traveling at subliminal speeds, do you see the correlations. So causality is preserved. Einstein's speed limit holds. But something deeply strange is happening beneath the surface of reality, something that suggests particles aren't truly independent objects, but are connected in ways that transcend ordinary space. What's actually happening when particles are entangled? This is where interpretations of quantum mechanics diverge again, offering different pictures of this spooky connection. In the Copenhagen interpretation, entangled particles share a single wave function, a single quantum state. Measuring one particle causes the wave function to collapse instantly, determining the state of both particles. It's not that information travels from one to the other, it's that they were never truly separate. They were always part of a unified quantum system, and measurement reveals correlated properties that were genuinely undetermined before observation. In the many worlds interpretation, when you measure one entangled particle, the universe branches. In one branch, you find spin up for the first particle and spin down for the second. In another branch, you find spin down for the first and spin up for the second. The correlations arise because the branches are correlated. When the universe splits, it does so in a way that preserves the entanglement. You always end up in a branch where the spins are opposite, not because anything travels between the particles, but because that's how the universal wave function evolves. There are also interpretations involving pilot waves, where particles have definite positions guided by a quantum wave that can extend across space, linking entangled particles through this guiding field. Or relational interpretations, where the properties of particles only exist relative to other systems. An entanglement reflects the fact that some properties are shared between multiple relations. Each interpretation offers a different ontological picture, a different story about what's really there, but all of them have to explain the same experimental results, the same spooky correlations. What makes entanglement particularly puzzling is that it seems to involve something like instantaneous connection, yet it can't be used for communication. If you could control what result you get when measuring an entangled particle, you could use entanglement to send signals faster than light. Measure your particle, force it into a particular state, and your partner far away would instantly know. But quantum mechanics doesn't allow this. The result of measuring a quantum system is random. You can't control whether you get spin up or spin down. You can only observe what nature gives you. So entanglement creates correlations, but not communication, a subtle distinction that preserves relativity while still allowing these strange quantum connections. Scientists have demonstrated entanglement not just with pairs of particles, but with larger groups, 3 particles, 4 particles, even collections of atoms or photons all entangled together in complex quantum states. These multi-particle entangled states are even stranger than simple pairs. They can exhibit correlations that seem to violate locality in multiple ways at once, creating a web of quantum connections that challenges any classical understanding of separated objects. An entanglement isn't just a curiosity. It's the foundation for emerging technologies like quantum computing and quantum cryptography. Quantum computers use entangled qubits to perform certain calculations exponentially faster than classical computers. The entanglement allows quantum information to be processed in parallel across many possibilities simultaneously, exploring vast solution spaces in ways classical bits never could. It's still early days. Quantum computers are finicky, requiring extreme cold and isolation from environmental disturbances. But the potential is enormous. Quantum cryptography uses entanglement to create perfectly secure communication channels. If 2 people share entangled particles and use them to encode messages, any attempt to eavesdrop will disturb the entanglement and be detected. It's security guaranteed by the laws of physics, not just by the difficulty of breaking codes. Banks and governments are already starting to use quantum cryptography for sensitive communications, relying on the spooky action Einstein doubted to protect their information. But beyond the applications, entanglement raises deep questions about the nature of reality. If particles can be connected across space in this way, what does that say about space itself? Maybe space isn't as fundamental as we think. Maybe at the deepest level, reality is about relationships and correlations, and space is just a way those relationships manifest at larger scales. Some physicists exploring quantum gravity have suggested that space-time itself might emerge from entanglement, that the fabric of space is woven from quantum correlations between fundamental degrees of freedom we don't yet fully understand. There's also a philosophical puzzle about when entanglement happens and how widespread it is. When two particles interact, they typically become entangled to some degree. And since particles are constantly interacting, light hitting your skin, air molecules bouncing off each other, atoms in solids vibrating together, entanglement should be everywhere. In principle, everything that has ever interacted is entangled with everything else, creating a vast web of quantum correlations spanning the universe. We're all entangled with the light we've emitted, the air we've breathed, the surfaces we've touched. Most of these entanglements decohere quickly, becoming so scrambled and diluted that they're effectively lost. But in principle, the quantum state of the universe is one enormous entangled system, and you're part of it. Every atom in your body has interacted with countless other atoms and particles over time, creating correlations that spread outward like ripples in a quantum pond. In a sense, you're not a separate object, but a pattern of correlations within the universal quantum state, temporarily cohering into something recognizable as a person before eventually dissolving back into the cosmic entanglement. It's a dizzying thought, lying there in the darkness. You feel separate, distinct, bounded by your skin, but quantum mechanically, you're connected to everything you've ever touched, every photon of light that's bounced off you, every molecule of air you've exhaled. The boundaries are fuzzy at the quantum level. You're less like a billiard ball and more like a wave in an ocean, a local intensification of correlations in a sea of quantum entanglement that extends across the cosmos. And yet, for all the strangeness of entanglement, for all the philosophical puzzles it creates, it's real. Experiments confirm it. Technologies use it. Nature doesn't care whether we find it spooky or counterintuitive. Particles become entangled. Measurements reveal correlations that transcend classical locality, and the universe operates according to quantum rules that challenge our everyday notions of separate objects existing independently in space. Einstein spent the last decades of his life searching for a unified field theory that would eliminate the randomness and non-locality of quantum mechanics. He never found it. He never accepted that the universe could work the way quantum mechanics said it did. And yet, nature proved him wrong on this point. The universe is quantum. Entanglement is real. Spooky action at a distance isn't just possible. It's fundamental to how reality operates at small scales. There's something oddly poetic about this. The universe refuses to be neatly separated into independent parts. Everything that interacts becomes correlated, linked in ways that persist even when the objects move far apart. It's almost as if the universe values connection over separation, correlation over independence. At the quantum level, isolation is impossible. We're all in this together, entangled with each other and with the cosmos in ways we're only beginning to understand. Perhaps there's comfort in that. You're not alone, not really. You're part of an interconnected quantum whole, linked to everything through invisible correlations, participating in a cosmic dance of entangled states. The boundaries between you and the rest of the universe are more permeable than they seem. You're not a separate thing, but a pattern within a larger pattern, a local clustering of quantum correlations that experiences itself as an individual, but is fundamentally inseparable from the whole. Let that sink in gently. Entanglement connects. Space doesn't isolate. Particles that interact remain linked. And in some deep quantum sense, everything is correlated with everything else, bound together in a web of relationships that transcends distance and challenges our intuitions about what it means to be separate. It's beautiful if you let yourself feel it. Strange, certainly. Spooky, as Einstein said, but also somehow comforting. Connection, woven into the fabric of reality itself. Take a breath. Let it rest. The quantum world does its entangling dance, particles correlate and decohere, and the universe remains stubbornly non-local despite our classical expectations. For tonight, that's enough. The mystery can wait. The entanglement persists, whether we understand it or not. Now let's turn our attention to the night sky, to the billions of stars you can't see from your bed, but which exist nonetheless, scattered across the darkness like grains of sand on a cosmic beach. Our galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars. Many, perhaps most, have planets orbiting them. Some of those planets must be in the habitable zone, at the right distance from their star for liquid water to exist. And with billions of planets, and billions of years of cosmic history, surely life must have arisen elsewhere. Surely we're not alone. And yet, we see no evidence of other civilizations, no radio signals, no megastructures, no visiting spacecraft. The universe appears empty of intelligent life, at least as far as we can tell. This is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked over lunch one day in 1950, "Where is everybody?" It's a simple question with profound implications. If the universe is so vast, so old, so full of potentially habitable worlds, why haven't we detected any signs of extraterrestrial intelligence? Why does the cosmos seem so quiet, so devoid of the chatter you'd expect from a galaxy teeming with civilizations? The silence is sometimes called the Great Silence, and it's one of the most puzzling observations in all of astronomy. Or perhaps more accurately, the most puzzling non-observation. Let's think about the numbers for a moment, gently, without hurry. The universe is about 13.8 billion years old. Our solar system is about 4.6 billion years old, which means the universe had been around for more than 9 billion years before our sun even formed. There are stars much older than ours, some nearly as old as the universe itself. If planets formed around those ancient stars, and if life emerged on some of those planets, and if some of that life evolved intelligence, then by now, right now, as you lie there could be civilizations billions of years more advanced than us. What could a civilization accomplish with a billion-year head start? We've had technology for maybe a few hundred years, and already we've gone from steam engines to spacecraft, from telegraphs to the internet. Imagine 1,000,000 years of progress, 100 million, 1 billion. Such a civilization would have capabilities we can barely imagine, technologies that would seem like magic to us. They might have spread across the galaxy, colonizing star systems, building vast structures, leaving unmistakable signs of their presence. And yet, when we look up, we see nothing obvious. No Dyson spheres blocking out starlight. No synchronized pulses from communication networks. No probes visiting our solar system to say hello. There have been many proposed solutions to the Fermi Paradox, dozens of possible explanations for the Great Silence, and none of them are entirely satisfying. Let's wander through some of the more prominent ones, gently, like walking through a garden of speculative possibilities. Perhaps life is extraordinarily rare. Maybe the origin of life, which we discussed earlier, is so improbable that it's only happened once, or a handful of times in the entire galaxy. Earth might be special, blessed with just the right combination of conditions, the right distance from the sun, the right-sized moon to stabilize its tilt, the right mix of elements, Jupiter in the outer system to deflect asteroids. Maybe what seems like it should be common is actually vanishingly rare, and we're one of the lucky few. This is called the rare Earth hypothesis, and it suggests that while simple life might be common, complex multicellular life like Earth's is exceptional. Or maybe life is common, but intelligence is rare. Life on Earth existed for billions of years before anything resembling intelligence emerged. For most of our planet's history, life was single-celled. Multicellular organisms only appeared about 600 million years ago. Complex brains are even more recent. Maybe the leap from simple life to technological civilization requires so many unlikely steps, so many contingent events, that it almost never happens. Intelligence might not be an inevitable outcome of evolution, but a fluke, a particular path that evolution stumbled down on Earth but rarely explores elsewhere. Perhaps civilizations don't last long. Maybe there's something called the Great Filter, some barrier that prevents most species from becoming long-lasting, spacefaring civilizations. The filter could be behind us, something we've already passed, like the origin of life or the development of intelligence. Or it could be ahead of us, something waiting to destroy us before we spread beyond Earth. Nuclear war, climate change, runaway artificial intelligence, asteroid impacts. There are plenty of ways a technological civilization might destroy itself. Maybe every civilization reaches a point where its technology becomes dangerous, and most don't survive the transition. We're alone not because life is rare, but because advanced life tends to be short-lived. It's a sobering thought, lying there in the quiet. Maybe the galaxy is full of ruins, dead worlds where civilizations rose and fell, leaving nothing behind but radioactive wastelands and silent cities. Maybe we're looking at a universe littered with cautionary tales, with species that didn't solve their problems in time, that let their conflicts, or their waste, or their creations destroy them before they could reach the stars. And maybe we're next, unless we're very careful, very lucky, or very wise. Or perhaps civilizations do survive, but they don't expand. Maybe there's no drive to colonize the galaxy. Maybe advanced species stay home, content with their own star system, uninterested in the vast expense and effort of interstellar travel. Or maybe they go virtual, uploading themselves into simulations where they can create entire universes more interesting than physical space. Why bother with the slow, dangerous work of building starships when you can explore infinite digital realms from the comfort of your home planet? Maybe the galaxy is full of civilizations that have turned inward, lost in virtual worlds of their own creation, never bothering to announce their presence to the cosmos. Then there's the zoo hypothesis, which suggests that advanced civilizations know about us, but are deliberately staying hidden, observing us like anthropologists studying an uncontacted tribe, waiting to reveal themselves until we reach some threshold of development. It's a comforting idea in some ways. We're not alone, just quarantined, protected from culture shock until we're ready for contact. But it also feels a bit like wishful thinking, and it raises questions about why such a policy would be universally followed. Surely at least one civilization would break the silence, would reach out or visit or make their presence known, even if others chose to remain hidden. Or maybe they're here already, and we just don't recognize them. Maybe intelligence doesn't always look like us, doesn't build radio telescopes or spaceships, doesn't communicate in ways we'd notice. Maybe it's distributed in networks we'd mistake for natural phenomena, or exists at scales too large or too small for us to perceive as intelligence. Maybe we're like ants, trying to understand the internet. The signals pass through us constantly, but we lack the conceptual framework to recognize them as communication. Some physicists have proposed that advanced civilizations might leave our universe entirely, migrating to other dimensions or different branches of the multiverse where physical laws are more favorable for computation or consciousness. Or maybe they create their own universes, baby universes budding off from ours, and all the advanced intelligences have moved into custom-designed cosmos where they can set the parameters to their liking. The great silence, in this view, isn't because we're alone, but because everyone more advanced than us has moved elsewhere, leaving the visible universe to primitive species like ours. There's also the possibility that we're actually early. Despite the universe being 13.8 billion years old, conditions for life might not have been favorable until relatively recently. The early universe was full of energetic processes, supernovae, gamma-ray bursts, active galactic nuclei that would have sterilized planets regularly. Heavy elements needed for complex chemistry only built up over time as generations of stars lived and died. Maybe only in the last few billion years has the universe settled down enough for technological civilizations to emerge. If so, we might be among the first, not tragically late but surprisingly early. The galaxy might be silent, not because everyone else is dead or hidden, but because we're pioneers, among the first to ask these questions. That's a strange thought, isn't it? To be among the first conscious beings to look up at the stars and wonder. To be early in a universe that will exist for trillions more years, with countless civilizations yet to come. It's lonely in a different way, but also special. If we're early, then maybe we have a responsibility to survive, to spread, to be the ancestors that future civilizations will wonder about. Maybe the great silence is an opportunity, not a mystery, a chance to be first, to shape the galaxy's future, to ensure that intelligence and consciousness persist and flourish throughout the cosmos. But maybe the answer is simpler and sadder. Maybe space is just too big. The distances between stars are so vast that interstellar travel is effectively impossible, or at least so difficult that no one bothers. Even traveling at a substantial fraction of light speed, crossing the galaxy would take hundreds of thousands of years. Sending radio signals is cheaper, but they weaken with distance, spreading out across space until they're indistinguishable from background noise. Maybe we're all out there, scattered across the galaxy, each species calling into the void, but the void is so enormous that our voices never reach each other. Maybe the universe isn't empty of intelligence, it's just too large for intelligence to meet. Or maybe we're simply not looking in the right way. We've been searching for radio signals, for signs of technology similar to ours. But what if advanced civilizations use communication methods we haven't discovered yet? Quantum entanglement communication, gravitational wave modulation, neutrino beams. There are speculative possibilities we can't detect because we don't have the right instruments or even the right theories. We're listening for drums in a world that's moved on to fiber optics. We're searching in the electromagnetic spectrum when the real conversation is happening in channels we haven't even imagined. The search continues, of course. SETI, the search for extraterrestrial intelligence, keeps listening, scanning the skies for artificial signals. Astronomers look for biosignatures in the atmospheres of exoplanets, signs of oxygen and methane that might indicate life. We send out our own messages, though they've barely left our cosmic neighborhood. The Voyager probes carry golden records with sounds and images from Earth, floating through interstellar space, unlikely to be found but carrying our greetings just in case. And we keep asking the question, where is everybody? The answer, whatever it is, will tell us something profound about our place in the universe. If we find evidence of other civilizations, it will be one of the most important discoveries in human history, proof that we're not alone, that intelligence and consciousness are common threads in the cosmic tapestry. But if we don't, if the silence persists, that's also meaningful. It suggests either that we're special, rare, precious, possibly unique, or that something prevents intelligence from lasting or spreading. Either conclusion should change how we see ourselves and our future. Lying there in the darkness, you might feel the weight of that silence. Hundreds of billions of stars in our galaxy, trillions of galaxies in the observable universe. And as far as we can tell, nobody else is home. Or at least, nobody's answering. The cosmos is vast and quiet, full of light and matter, but apparently empty of voices other than our own. It's awe-inspiring and lonely, wondrous and troubling all at once. But maybe the silence won't last forever. Maybe tomorrow, or next year, or in a century, we'll detect a signal. A pattern in the cosmic noise that couldn't be natural. A message from someone out there saying, we're here too. Or maybe we'll remain alone, the only consciousness in a vast, beautiful, indifferent universe, left to make our own meaning, to create our own purpose, to decide what to do with our brief moment of awareness in the cosmic dark. For now, the paradox remains. The universe seems suitable for life, yet we see no life. It seems conducive to intelligence, yet we detect no intelligence. And we're left wondering whether we're truly alone, whether we're early, whether we're looking in the wrong way, or whether there's some great filter ahead that we haven't reached yet. The question hangs in the air, unanswered. waiting patiently for evidence to tip the scales one way or another. Let it rest. The stars will still be there tomorrow, still silent, still mysterious. The search continues, whether you're awake or asleep, whether you're pondering the question or dreaming peacefully. And somewhere, perhaps, in some other corner of the galaxy, someone else might be lying in the darkness, looking up, asking the same question. Where is everybody? And maybe, just maybe, wondering if we're out here too. Let's drift back to the beginning now, to the very first moments after the Big Bang, to a time when the universe was unimaginably hot and dense, when everything that would ever exist was compressed into a space smaller than an atom. We're going to explore a problem that puzzled cosmologists for decades, a problem so perplexing that the solution proposed to fix it sounds more like science fiction than science, and yet, it might be true. This is the story of the horizon problem and cosmic inflation, a tale of how the universe might have expanded faster than light in its first fraction of a second, and why that strange idea has become one of the pillars of modern cosmology. First, let's understand the problem. When we look at the cosmic microwave background, that faint glow of radiation left over from when the universe was only 380,000 years old, we see something remarkable. The temperature is almost perfectly uniform in all directions. No matter where you point your telescope, the universe looks the same temperature to within 1 part in 100,000. That might not sound strange at first, but it is. It's very strange indeed. You see, temperature uniformity requires thermal equilibrium. If you put a hot object next to a cold object, heat flows from hot to cold until they reach the same temperature. That's what equilibrium means. Things have had time to exchange energy and even out. But for the early universe to have such uniform temperature, different regions would have needed to be in contact, to exchange energy, to reach equilibrium together. And here's the problem. According to standard Big Bang cosmology, they never had time to do that. Light, and nothing can travel faster than light, only had 380,000 years to cross the universe by the time the cosmic microwave background was emitted. In that time, light could have traveled about 380,000 light years, so regions of space separated by more than this distance couldn't have communicated with each other, couldn't have exchanged heat, couldn't have reached thermal equilibrium. And yet, when we look at regions of the cosmic microwave background that are separated by much greater distances, regions that should never have been in contact, we find they have the same temperature. How? This is called the horizon problem. The horizon, in this context, is the maximum distance light could have traveled since the Big Bang. Regions beyond each other's horizons are causally disconnected. They can't have influenced each other because no signal could have passed between them. And yet the entire observable universe, all these causally disconnected regions, somehow conspire to have the same temperature. It's as if you walked into a vast auditorium where everyone is wearing the same shade of blue, but nobody communicated with each other beforehand. The coincidence seems too perfect to be random. There are other problems with the standard Big Bang model too. There's the flatness problem. The universe appears to be spatially flat, not curved, to an extraordinary degree of precision. But flatness is unstable. A universe that starts out even slightly curved becomes more curved over time. For our universe to be as flat as it is today, it would have had to start out flat to within 1 part in 1060 at the Planck time, the earliest moment we can describe with physics. That's a level of fine-tuning that makes the cosmological constant problem look modest. Why would the universe start out so precisely flat? And there's the monopole problem. Grand unified theories of particle physics predict that the early universe should have produced vast numbers of magnetic monopoles, particles with only a north or south magnetic pole, not both. We've never observed a single one. Where are they all? These problems vexed cosmologists through the 1970s. The Big Bang model worked wonderfully for explaining the expansion of the universe, the formation of light elements, the existence of the cosmic microwave background. But it had these nagging issues, these initial conditions that seemed unnaturally fine-tuned. these predictions that didn't match observations. Something was missing. Then, in 1980, a young physicist named Alan Guth had an idea. What if, in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion? Not just fast, exponentially fast, doubling in size every 10:37 seconds or so. In a period lasting perhaps 10:32 seconds, a region of space smaller than a proton would have inflated to the size of a grapefruit, or larger. Space itself stretched, carrying everything with it, expanding faster than the speed of light. Wait, faster than light? Doesn't that violate relativity? Not quite. Special relativity says nothing can travel through space faster than light. But it doesn't limit how fast space itself can expand. Space can stretch as fast as it wants, carrying galaxies and light and everything else along for the ride. During inflation, space expanded so rapidly that regions which had been in causal contact, which had reached thermal equilibrium, were suddenly separated by vast distances. The horizon expanded much faster than light could travel, separating regions that had once been neighbors. This solves the horizon problem elegantly. Before inflation, the entire observable universe was a tiny region, small enough that light could cross it many times, establishing thermal equilibrium. Then inflation stretched that tiny equilibrated region to cosmological scales. The regions we see as causally disconnected today were actually in contact before inflation. They reached the same temperature back then, and inflation simply spread them out. The uniformity of the cosmic microwave background isn't a coincidence. It's a consequence of the universe starting small enough for equilibrium to establish, then inflating to large scales. Inflation also solves the flatness problem. Any curvature in space gets smoothed out by exponential expansion, just like inflating a balloon makes its surface appear flatter. If you blow up a balloon to the size of Earth, any ant on its surface would perceive it as flat. The curvature becomes undetectable at small scales. Similarly, inflation stretched the universe so much that any initial curvature became negligible. The universe appears flat today, not because it started out incredibly flat, but because inflation flattened it. And the monopole problem? Inflation diluted them. If monopoles formed before inflation, they were spread out over such vast distances that we'd never expect to find one in our observable universe. They exist, perhaps, but they're scattered so thinly across the inflated cosmos that encountering one is vanishingly unlikely. It's an elegant solution, almost suspiciously so. One mechanism, inflation, solves multiple problems at once. But what caused inflation? What made space expand so rapidly? The most common answer is that inflation was driven by a scalar field called the inflaton field, permeating all of space. This field had potential energy, and as the universe cooled, the field was stuck in a high-energy state, a false vacuum. While stuck there, the vacuum energy acted like a cosmological constant, driving exponential expansion. Eventually, the field rolled down to its true, minimum energy state. Inflation ended, and the field's potential energy converted into ordinary matter and radiation, what's called reheating. The hot, dense state we normally associate with the Big Bang was actually the end of inflation, not the true beginning. It sounds speculative, and it is. We don't know what the inflaton field is, or whether it's related to any fields in the standard model of particle physics. We've never detected it directly. Inflation is a hypothesis, a framework that explains observations and makes predictions, but it's not yet confirmed in the way we'd like. However, it makes testable predictions. Inflation should have produced tiny quantum fluctuations in the density of the early universe, fluctuations that got stretched to cosmic scales and eventually seeded the formation of galaxies. We see these fluctuations imprinted in the cosmic microwave background, their amplitude and distribution matching inflationary predictions remarkably well. Inflation also predicts gravitational waves produced during the inflationary epoch, stretching along with space, leaving subtle polarization patterns in the cosmic microwave background. Detecting these primordial gravitational waves would be a smoking gun for inflation, direct evidence that this exponential expansion really happened. Scientists have been searching for this signal for years, using increasingly sensitive telescopes at the South Pole and in Chile. In 2014, there was a false alarm, a detection that turned out to be contaminated by dust in our own galaxy. But the search continues, patiently, hopefully. There are also puzzles within the inflationary framework. What came before inflation? Was there a beginning, or has the universe been inflating eternally, with our Big Bang just one of countless bubble universes forming within an eternally inflating background? Some versions of inflation, called eternal inflation, suggest that once inflation starts, it never completely stops. Quantum fluctuations cause some regions to stop inflating and reheat, forming universes like ours, while other regions keep inflating, spawning more bubble universes. The result is a fractal multiverse, an infinite ensemble of pocket universes, each with potentially different physical laws, emerging from an eternally inflating background. This leads to profound philosophical questions. If eternal inflation is correct, then our universe is just one bubble in an infinite foam of universes. Everything that can happen does happen, somewhere in the multiverse. There are infinitely many versions of you, infinitely many variations on cosmic history, infinitely many ways physical laws could be configured. Some physicists find this beautiful, a theory that explains everything by generating all possibilities. Others find it troubling, a theory that explains too much and therefore explains nothing, making testability difficult or impossible. There are also alternative theories. Cyclic models propose that the universe undergoes repeated cycles of expansion and contraction, with each Big Bang followed eventually by a big crunch and a new bounce. These models avoid the singularity at the beginning of time by suggesting there is no beginning, just an eternal cycle of death and rebirth. Or there are theories involving colliding brains in higher dimensional spaces, where our universe is a three-dimensional membrane floating in a higher dimensional bulk, and the Big Bang was the result of our brain colliding with another. These alternatives aren't as developed as inflation, and they have their own problems, but they remind us that science remains open, that the question of cosmic origins isn't settled. Lying there, you might find something oddly soothing about inflation. The idea that the entire observable universe, with its hundreds of billions of galaxies, all inflated from a region smaller than a proton. You, your room, the Earth, the Sun, the entire Milky Way, the distant galaxy clusters, all of it started out in a space too small to see, all causally connected, all in thermal equilibrium, before being stretched to cosmic proportions in a fraction of a second. It's absurd, in a way. Wonderfully absurd. And yet the evidence points to something like this having happened. The universe has a story, a history written in the patterns of radiation and the distribution of galaxies. And that story begins with a moment of exponential expansion, a brief instant of cosmic inflation that set the stage for everything that followed. The hot Big Bang, the formation of particles, the synthesis of elements, the birth of stars and galaxies, the formation of planets, the origin of life, the evolution of consciousness. All of it traces back to that first fraction of a second, when space itself expanded faster than light, smoothing out wrinkles, diluting relics, and planting the seeds from which structure would eventually grow. We can't observe inflation directly. It happened too long ago, at energies too high for us to recreate. But we can see its effects, read its signature in the cosmic microwave background, test its predictions against increasingly precise data. And so far, everything points to inflation being right, or at least very close to right. The details might change, the mechanism might be refined, but the basic picture of an early period of exponential expansion seems increasingly secure. There's a beauty to this, a kind of cosmic poetry. The universe remembers its beginning, carries evidence of its earliest moments in the structure of space and time, and we, tiny creatures on a small planet, can read that evidence, reconstruct what happened, understand the story of how everything came to be. It's one of humanity's greatest achievements, really, this ability to look at patterns in light and deduce the history of the cosmos. Let that thought settle softly. The universe inflated, space stretched faster than light, problems dissolved, mysteries deepened, and a new picture of cosmic origins emerged. Whether it's the complete story or just a chapter remains to be seen. But for now, inflation stands as our best explanation for why the universe looks the way it does, why it's flat and uniform and full of structure. And that's something, even if we're still working out the details. Take a breath. The inflating universe can rest for tonight. It's not going anywhere, or rather, it's still going everywhere, still expanding, though much more sedately now than in those first fractions of a second. For tonight, just let the mystery wash over you, peaceful and profound. The cosmos has secrets, but it also has answers, if we're patient enough to listen. Let's come back down to Earth now, away from cosmic mysteries and quantum puzzles, and look at something you encounter every single day without thinking about it. Flowing fluids, water pouring from a tap, air moving past your hand when you wave it, cream swirling in coffee. These seem like simple things, ordinary phenomena that happen all around you constantly. And yet, turbulence, the chaotic, swirling motion that fluids develop when they flow fast enough, is one of the great unsolved problems in classical physics. It's a problem so difficult that physicist Richard Feynman once said, it was the most important unsolved problem of classical physics. And Werner Heisenberg, when asked what he would ask God given the chance, reportedly said he would ask about turbulence, not quantum mechanics. Think about smoke rising from a candle. At first, it rises in a smooth, laminar stream, flowing upward in neat layers. But then, after a few inches, something happens. The flow becomes chaotic. Eddies form. The smoke swirls and twists and breaks into smaller and smaller vortices, creating that familiar, mesmerizing dance of turbulent motion. What triggers this transition? Why does smooth flow suddenly become turbulent? And once turbulent, why does the motion look the way it does? Structured yet chaotic, patterned yet unpredictable. We've been studying fluid mechanics for centuries. The equations that govern fluid flow, the Navier-Stokes equations, have been known since the 1800s. These equations describe how velocity, pressure, and density change in a flowing fluid, accounting for viscosity and external forces. They're partial differential equations, mathematical expressions relating spatial and temporal derivatives, and they're notoriously difficult to solve, except in the simplest cases. But we have them. We know the rules fluids follow. And yet, we can't predict turbulence. The problem is that turbulence is a non-linear phenomenon. The Navier-Stokes equations are non-linear. The rate of change of velocity depends on velocity itself, creating feedback loops and complexity. Small perturbations can grow, cascade into different scales, interact in intricate ways. A tiny disturbance in the flow can amplify, triggering instabilities that break smooth flow into turbulent chaos. And once turbulence develops, it exhibits behavior across many scales simultaneously. Large swirls breaking into smaller ones, which break into even smaller ones, creating a cascade of energy from large to small scales. This cascade is described by something called the Kolmogorov theory, developed by Russian mathematician Andrei Kolmogorov in 1941. The theory says that in fully developed turbulence, energy injected at large scales cascades down through progressively smaller scales until it reaches scales so small that viscosity can dissipate it as heat. The energy spectrum follows a particular power law. Smaller eddies have less energy, but there are more of them, creating a fractal-like structure. It's a beautiful statistical theory, and it matches observations reasonably well. But it's statistical. It tells you about average behavior, not about specific flows. It doesn't predict where vortices will form, how they'll interact, when turbulence will suddenly appear. You might wonder why we can't just simulate turbulence on a computer. After all, we have the equations. We have supercomputers. Why not just solve the Navier-Stokes equations numerically and see what happens? The problem is resolution. Turbulent flows contain structures at many different scales, from large eddies down to tiny dissipative scales. To simulate turbulence accurately, you need to resolve all these scales, which means using a grid fine enough to capture the smallest eddies. For realistic flows at high speeds, this requires impossibly fine grids. The number of grid points grows as the Reynolds number, a measure of how turbulent a flow is, to the power of 9.4. For flows like those around aircraft or in Earth's atmosphere, you'd need more grid points than atoms in the observable universe. It's computationally intractable. So we use approximations. We model the small scales statistically, resolving only the large ones explicitly. This works reasonably well for engineering purposes. We can design aircraft and predict weather and model ocean currents to useful accuracy. But it's not a fundamental understanding. We're patching over our ignorance with empirical models, adjusting parameters to match observations, hoping we've captured the essential physics without fully understanding why the approximations work. And then there's the mathematical question. Do solutions to the Navier-Stokes equations always exist, and are they always smooth? This is one of the Millennium Prize problems, with $1 million reward for whoever solves it. The question is whether, given reasonable initial conditions, the equations always produce physically meaningful solutions that don't blow up to infinity or develop singularities. For three-dimensional turbulent flow, we don't know. It's possible that under certain conditions, the equations predict that velocity or vorticity becomes infinite in finite time, a physical impossibility, suggesting either that turbulence can't be described by these equations alone, or that some additional physics comes into play at extreme conditions. Most physicists believe the equations are fine, that solutions remain smooth and bounded. Viscosity should prevent infinities by smoothing out sharp gradients. But proving this rigorously has eluded mathematicians for decades. It's a humbling situation. We have equations that work beautifully in practice, but can't prove they always make mathematical sense. It's like having a recipe that produces delicious meals, but not being able to prove the recipe won't occasionally tell you to do something impossible. Turbulence appears everywhere in nature. The atmosphere is turbulent, creating the chaotic weather patterns that make forecasting difficult beyond a week or two. Ocean currents are turbulent, mixing nutrients and heat across vast scales. Stars have turbulent interiors, with convective motions that transport energy outward. Even your bloodstream is turbulent in the aorta and major arteries, creating complex flow patterns that affect how efficiently oxygen is delivered to tissues. Understanding turbulence would have profound practical implications for weather prediction, climate modeling, aircraft design, medical devices, energy generation, nearly every field that deals with flowing fluids. There's something almost philosophical about turbulence, a sense that it represents a limit to what we can know. Deterministic chaos, they call it. The equations are deterministic, they don't involve randomness, yet the solutions are so sensitive to initial conditions that they're effectively unpredictable. Change the initial state by an infinitesimal amount, and after a short time, the flow looks completely different. This is the famous butterfly effect. A butterfly flapping its wings in Brazil might, in principle, affect weather patterns in Texas weeks later. Not because the butterfly's wings exert significant force, but because tiny perturbations can cascade through a nonlinear system, amplifying into large-scale changes. This sensitivity makes long-term prediction impossible, even in principle. It's not a matter of better computers or more precise measurements, it's fundamental. Turbulent systems are inherently unpredictable beyond a certain time horizon, no matter how much we improve our tools. We can understand them statistically, describe their average behavior, predict probabilities. but the specific details remain out of reach, lost in the chaos of nonlinear interactions. Lying there, you might reflect on the irony. We can predict the motion of planets centuries into the future with extraordinary precision. We can calculate the behavior of quantum systems, track particles in accelerators, model the evolution of the universe. But we struggle to predict how smoke will swirl from a candle or how water will flow past a rock in a stream. The everyday, the familiar, the seemingly simple, turbulence, remains mysterious in ways that distant galaxies and elementary particles are not. Maybe that's fitting. Maybe the universe is telling us that complexity doesn't require exotic conditions or extreme energies. You don't need black holes or quantum entanglement to encounter deep mysteries. You just need water moving fast enough, air flowing past an obstacle, fluids doing what fluids do. Turbulence is accessible, observable, present in your everyday experience, and yet it's as profound a puzzle as anything in physics. There have been attempts to find underlying structure in turbulence, to identify coherent patterns that persist within the chaos. Scientists have discovered that turbulent flows contain what are called coherent structures, organized patterns of vorticity that appear repeatedly, that survive for long times before breaking up or merging. These structures have shapes and dynamics that seem almost universal, appearing in different types of turbulent flows. But why they form, how they interact, what determines their lifetimes, these questions remain partially answered at best. Some researchers have looked at turbulence from the perspective of dynamical systems theory, trying to identify attractors and unstable periodic orbits in the space of possible flow states. The idea is that turbulent flow is wandering through a complex landscape of possible states, occasionally passing near certain special configurations. If we could map this landscape, catalogue these special states, we might gain insight into the structure underlying the chaos. It's a promising direction, but progress is slow. The state space is infinite dimensional, the dynamics are ferociously complex, and extracting general principles from specific calculations is difficult. Others have approached turbulence through symmetry and invariance, looking for conserved quantities and transformations that leave the equations unchanged. Turbulence breaks many symmetries. It's not time reversible, not spatially uniform, not isotropic. But there might be hidden symmetries, statistical regularities that emerge at certain scales or under certain conditions. Finding these could provide organizing principles, ways to simplify the complexity without losing the essential physics. There's also the question of whether turbulence might be connected to deeper questions about information, entropy, and thermodynamics. Turbulence generates entropy, dissipating organized kinetic energy into random thermal motion. It's an irreversible process, one that clearly has an arrow of time. You can tell which direction time flows by watching turbulence develop and dissipate. Maybe understanding this irreversibility more deeply would shed light on both turbulence and the arrow of time we discussed earlier. Maybe they're linked, both arising from the same fundamental principles about how information and energy flow in complex systems. For now, turbulence remains partially understood, partially mysterious. We can describe it statistically. We can simulate it approximately. We can work with it pragmatically in engineering and meteorology and medicine. But we can't claim to fully understand it, can't solve the equations exactly, can't predict its detailed behavior. It's a reminder that classical physics, despite being centuries old and incredibly successful, still has open questions, still has phenomena that resist complete understanding. And perhaps that's all right. Perhaps turbulence, in its chaotic beauty, is teaching us something about the limits of knowledge, about the nature of complexity, about how deterministic rules can produce unpredictable outcomes. Perhaps it's reminding us that the world is richer than our equations, that mathematics, for all its power, sometimes struggles to capture the fullness of physical reality. Or perhaps it's just hard, a problem that will eventually yield to better mathematics, better computers, better physical insight, but hasn't yet. For tonight, let the turbulence rest. Let the smoke swirl in your imagination, the water flow past obstacles, the air move in its chaotic patterns. It's been doing this for billions of years, long before we arrived to puzzle over it, and it will continue long after we're gone. The mystery persists, beautiful and frustrating in equal measure, accessible yet elusive, familiar yet profound. Take a breath. Let it flow, smoothly or turbulently, in and out of your lungs. Your body deals with fluid mechanics constantly, moving blood and air and lymph, never thinking about the equations, never worrying about Reynolds numbers or Kolmogorov scales. It just flows, as fluids do, following the same equations we can't fully solve, creating the same patterns we can't fully predict. And somehow, that's enough. Life doesn't wait for us to understand turbulence. It simply flows. And so we arrive at perhaps the deepest mystery of all, one that threads through everything we've discussed tonight, the nature of time. What is it really? We've talked about time's arrow, about how it seems to flow in one direction. We've discussed space-time and how gravity curves it. We've mentioned how quantum mechanics treats time differently than space. But we haven't directly confronted the central question: what is time? Does it flow, or do we just experience it as flowing? Does it exist independently of the events that happen in it? Or is it merely a relationship between those events? Is time fundamental, or does it emerge from something more basic? These questions have puzzled philosophers for millennia and physicists for centuries, and we're no closer to definitive answers today than Aristotle was in ancient Greece. Time is both the most familiar aspect of our experience and the most mysterious. You feel it passing right now, this moment slipping into the past as the next moment becomes the present. But what makes this moment now? Why does the present feel different from the past and future? And why, in all our physical equations, is there nothing special about the present moment at all? In physics, time is usually treated as a coordinate, a dimension similar to the three spatial dimensions, forming together the four-dimensional fabric of space-time. Einstein's relativity unified space and time, showing that they're not separate entities, but aspects of a single geometric structure. Events in space-time have coordinates, 3 for space, 1 for time, and the geometry tells matter how to move, and matter tells geometry how to curve. It's elegant, mathematically beautiful, and extraordinarily successful at making predictions. But it treats time as just another dimension, no different in kind from left-right or up-down. Yet time feels different. You can move freely in space, turn around, step backward, take any path you like, but you can't choose your direction in time. You move forward, always forward, at 1 second per second, unable to pause or reverse or skip ahead. Why? What makes time special? What gives it this unique, directional character that space doesn't have? One answer is thermodynamic. Time's direction is defined by the increase of entropy, the tendency for systems to move toward disorder. We discussed this when talking about the arrow of time. The future is the direction of higher entropy. The past is where entropy was lower. This gives time a direction, an arrow, but it doesn't really explain what time is. It just correlates the direction of time with a statistical property of matter. And it raises the question, if entropy is what defines time's direction, then in regions where entropy isn't increasing, does time not flow? In a perfectly isolated system at equilibrium, where entropy is maximized and unchanging, does time stop? That seems absurd, yet the logic follows from identifying time's arrow with entropy's increase. Maybe time is more fundamental than entropy, more basic than any physical process. Maybe it's a background in which events occur, an absolute framework independent of matter and energy. This is the Newtonian view. Time flows uniformly, at the same rate everywhere, regardless of what's happening. Newton called it absolute, true, and mathematical time, a time that flows equably without relation to anything external. It's an intuitive picture, matching how we experience time. Seconds tick by steadily, the same for everyone, providing a universal clock against which all motion is measured. But Einstein showed that this view is wrong. Time isn't absolute, it's relative, depending on motion and gravity. A clock moving fast runs slower than a stationary clock. A clock in a strong gravitational field runs slower than one in weak gravity. These aren't illusions or measurement errors. They're real effects, confirmed by countless experiments. Astronauts on the International Space Station age slightly slower than people on Earth. GPS satellites have to account for relativistic time dilation to maintain accuracy. Time genuinely runs at different rates in different places and for different observers. There's no universal clock, no absolute time flowing uniformly for everyone. So if time is relative, what is it relative to? What is it really, beyond coordinates in space-time and readings on clocks? Philosopher Julian Barber has argued that time doesn't exist at all, that it's an illusion arising from our perspective within the universe. In his view, the universe is a vast collection of possible configurations, what he calls nows, and what we experience as time is our path through these configurations, moving from one now to another. But there's no actual flowing, no becoming, just a sequence of static states that we interpret as temporal because our memories create a sense of continuity. It's a radical idea, and most physicists don't go that far. But there's something to it. In quantum mechanics, the Schrödinger equation describes how wave functions evolve over time, but the equation itself is timeless. It relates different moments without privileging any particular moment as now. In general relativity, space-time is a four-dimensional block, with past, present, and future all existing equally, laid out in geometric relationships. The equations don't distinguish between past and future in the way our experience does. They're time-symmetric, or nearly so. Where, then, does the flowing present come from? Perhaps it's a feature of consciousness, not physics. Perhaps the sensation of time flowing, of moments becoming and passing, is something our minds construct to make sense of causality and memory. We remember the past, but not the future, so we perceive ourselves as moving from a fixed past toward an open future. This creates the impression of flow, of a moving present advancing into uncharted territory. But physically, the future might already exist, laid out in the block universe, and our sense of moving through it is an artifact of how our brains process information sequentially. This view, called eternalism, or the block universe interpretation, suggests that all moments in time exist equally. The Big Bang exists. The moment you were born exists. The moment you're experiencing right now exists. The moment of your death exists. They're all equally real, all part of the four-dimensional tapestry of space-time. Nothing is becoming or passing away. It all simply is, timelessly, and we're four-dimensional objects stretched through time, with our past selves and future selves all existing simultaneously in the block. It's a strange thought lying there. If eternalism is true, then every moment of your life exists forever, in a sense. The moments of joy, of sorrow, of mundane daily routine, they're all permanent fixtures in space-time, never truly passing away, always there in their designated coordinates. You're not moving through time so much as existing through it, a four-dimensional worm with your birth at one end and your death at the other, and everything in between stretched out across the years. But then why do we experience time flowing? If all moments exist equally, why does it feel like the present is moving, like we're constantly transitioning from one moment to the next? This is sometimes called the problem of the now, explaining why one particular moment feels special, feels like now, when physics treats all moments as equal. Some philosophers argue that the now is irreducibly subjective, a feature of conscious experience that doesn't appear in physical descriptions of the world. Others say it's an illusion, a persistent trick of perception that doesn't correspond to anything real. Or maybe time does flow, and eternalism is wrong. Maybe presentism is correct, the view that only the present moment exists, that the past has ceased to be, and the future hasn't come into being yet. In this view, the universe is constantly becoming, new moments coming into existence as old ones vanish. Time genuinely flows, and we're surfing the edge of existence, the moving boundary between what has been and what will be. It matches our experience more closely, preserves the sense that the present is special, that choices we make now are genuinely open and not predetermined by an already existing future. But presentism has problems fitting with relativity. If only the present exists, which present? Relativity says there's no universal simultaneity, no objective way to say which events are happening now across the universe. What's present for you might be past or future for someone moving at a different velocity. Whose present is the real one? If all presents are equally valid, then maybe all moments exist after all, and we're back to something like eternalism. Perhaps the answer lies in quantum mechanics. Some interpretations suggest that the future is genuinely open, not yet determined, and quantum measurements cause reality to branch or collapse, actualizing possibilities into definite outcomes. In this view, the past is fixed, determined by the accumulation of quantum measurements that have already happened. The present is where new measurements occur, where possibilities collapse into actualities. And the future is a superposition of possibilities, not yet real, waiting to be determined by measurements not yet made. Time's flow, then, is the process of possibility becoming actuality, of quantum indeterminacy resolving into definite states. This fits nicely with our experience. The past feels fixed, unchangeable. The future feels open, undecided. The present is where choices happen, where possibilities are selected and alternatives are foreclosed. But it requires taking quantum mechanics seriously at large scales, applying it not just to particles, but to the entire universe, which is philosophically controversial and scientifically uncertain. There's also the possibility that time is emergent, not fundamental. Perhaps at the deepest level of reality, the Planck scale, where quantum gravity effects dominate, time doesn't exist. Perhaps there's only a timeless, quantum state, and time emerges at larger scales from the way that state is structured. This is a theme in some approaches to quantum gravity, like loop quantum gravity and causal set theory, where space-time itself is built from more fundamental discrete elements, and time as we know it is an approximate, coarse-grained description of how those elements relate to each other. If time is emergent, then asking what is time might be like asking what is temperature. Temperature isn't a fundamental property, it's a statistical feature of many particles moving around. Similarly, time might be a statistical or emergent feature of some more fundamental quantum structure. Below a certain scale, the question, what time is it, might not even make sense, like asking the temperature of a single atom. This could explain why quantum gravity is so difficult. We're trying to quantize something, time, that might not be fundamental, that might emerge only at scales larger than the Planck length. Trying to describe what happens at the Planck time might be asking a question that doesn't have an answer, because time itself breaks down there, dissolves into whatever more fundamental structure reality has at that scale. Whatever time is, we experience it. We age, we remember, we anticipate. Moments pass, or seem to, and we're carried along with them. The universe appears to evolve, to change, to have a history and a future. And even if physicists eventually decide that time is illusory or emergent or relative or something we haven't conceived yet, that won't change the lived experience of temporality. The fact that being conscious involves experiencing a sequence of moments, a before and after, a narrative arc from birth to death. Maybe that's enough. Maybe we don't need to fully understand time to live in it, to experience its passage, to make our peace with its inexorable flow. Maybe the mystery of time is meant to remain mysterious, a fundamental feature of existence that we can describe mathematically, measure precisely, but never quite grasp in its essence. Like consciousness, like existence itself, time might be one of those bedrock features of reality that we can't reduce further, can't explain in terms of something more basic, because there is nothing more basic. Time just is, and we exist in it, through it, aware of it, shaped by it. Lying there, you're experiencing time in its most direct form, the passage of moments, one after another. Seconds accumulate into minutes, minutes into hours. This recording progresses, moving from beginning toward end. Your breath follows its rhythm, in and out, a cyclical process marking time's passage. Your heartbeat counts the seconds, a biological clock that's been ticking since before you were born and will stop at some unknown future moment. You're embedded in time, constituted by it, unable to step outside it even for a moment. It's the water you swim in, so ubiquitous and essential that you rarely notice it, yet so fundamental that without it, nothing would make sense. And perhaps that's the deepest mystery, not what time is, but why there's a you to experience it, why the universe bothered to create beings who can wonder about time, who can reflect on its passage, who can feel nostalgia for the past and hope for the future. Time could flow without consciousness. Clocks could tick in an empty universe. Entropy could increase without anyone noticing. But instead, there are conscious beings, you among them, experiencing time's passage, marking its flow, creating meaning within its constraints. Maybe the universe needs observers to make time real. Maybe without consciousness to experience the present, to remember the past, to anticipate the future. Time would be like the sound of a tree falling, with no one to hear it, something that happens in a sense, but lacking the subjective reality that observation provides. Or maybe consciousness is just along for the ride, a byproduct of complex information processing that happens to experience time's flow without being essential to it. We don't know. We may never know. Time keeps its secrets well, revealing just enough for us to build clocks and write equations and navigate the world, but never quite enough for us to say with confidence what it ultimately is. And so we continue, experiencing time moment by moment, aging and changing and moving forward, wondering occasionally about the nature of the medium in which we exist, but mostly just living in it, accepting its passage, making the best of the time we have. Let it rest now. Time flows or doesn't flow, exists fundamentally, or emerges from something deeper, but either way, it carries you gently towards sleep, toward rest, toward the unconsciousness that temporarily suspends your experience of temporality. In sleep, time passes without your awareness, hours compressing into moments or expanding into dreams, your experience of time becoming fluid and strange. And then you'll wake, and time will resume its familiar forward march, and another day will begin, another sequence of moments to experience and navigate and eventually let go. For now, just be in this moment. Don't worry about what time is or how it works. Just experience it, this gentle now, this soft present that contains everything you are. The past is gone, the future hasn't arrived, and here you are, here and now, existing, conscious, experiencing time's passage in the most direct way possible. That's enough. That's everything, really. The moment, experienced, then released. The next moment, welcomed, then released in turn. Time flowing through you or you flowing through time, it hardly matters which. Just the experience, just the gentle progression from one moment to the next. Rest now. Let time carry you. The mysteries will still be there tomorrow. The universe will continue its expansion, entropy will increase, quantum states will collapse or branch, and time will keep doing whatever time does. You don't need to solve these problems tonight. You don't need to understand what time is or why it flows. You just need to be in it, to experience it, to let it carry you gently towards sleep and dreams and the quiet unconsciousness where time passes unmarked and unmeasured. The mysteries wait. time waits. And sleep, that temporary suspension of your conscious experience of temporality, waits patiently for you to surrender to it. What are the problems that have tricked scientists for years? It's the question that brought us here, whispered softly at the beginning, like a child asking if grown-ups know everything, if there are puzzles even the smartest people can't solve. And after wandering through time's arrow and dark matter's invisibility, through quantum measurements and conscious experience, through black holes and cosmic constants, through life's origins and particles' entanglement, through silent galaxies and inflating universes, through swirling fluids and time's essential nature, we find ourselves gently circling back to where we began, still wondering, still curious, perhaps even more awed by how much remains unknown. We've learned that time flows forward for reasons we don't fully understand, that most of the universe is made of substances we can't see or identify, that observation changes reality in ways we can't explain. We've explored how consciousness arises from matter in mysterious ways, how black holes might preserve or destroy information, how empty space has energy that defies our calculations by impossible margins. We've discovered that life emerged through processes we're still piecing together, that particles remain connected across any distance through quantum entanglement, that the cosmos seems empty of other voices for reasons we can only guess at. We've seen how the universe might have inflated faster than light in its first moments, how everyday turbulence resists our equations and computers, how time itself might be an illusion or emergence or something we lack concepts to properly describe. Maybe these problems don't have simple answers. Maybe they're doorways into deeper mysteries, each solution revealing 3 new questions. Maybe science is less about arriving at final truths and more about learning to ask better questions, to appreciate complexity, to marvel at how much the universe still has to teach us. Maybe that's the whole point, not to eliminate mystery, but to explore it thoughtfully, carefully, with curiosity and wonder, rather than fear or frustration. The universe doesn't owe us comprehensibility. The fact that we can understand anything at all is rather remarkable. So, with all of this in mind, are you still awake? If you are, I hope it's not because these mysteries were too interesting, too engaging, too stimulating to let you drift off. Though, if they were, well, at least you've spent this time learning about the beautiful puzzles that scientists continue to explore, the questions that keep some of the brightest minds awake at night, or in your case perhaps, that have accompanied you peacefully towards sleep. And if you're already halfway to dreamland, may your thoughts be filled with gently spinning galaxies and softly entangled particles, with time flowing like water and consciousness flickering like candlelight. Before you drift off completely, I'd love to know where you're listening from and what time it is in your part of the world. Drop a comment and share. Are you perhaps a student pondering these mysteries yourself, or someone who just finds unsolved scientific problems strangely relaxing? Are you listening from a quiet room in Stockholm at 2 a.m., or from a sunny afternoon in Sydney while pretending to work? Let me know. It's always such a joy to see this peaceful community scattered across the globe, all wondering together about the universe's deepest puzzles. If you found this gentle journey through science's greatest unsolved problems relaxing or informative, or both, please do consider giving this video a like and subscribing to Sleepy Science Student. It's a small gesture that helps me keep bringing you more calming, curious content from the world of science and beyond. More mysteries to ponder as you drift towards sleep. More questions to carry with you into dreams. Thank you for joining me on this journey through the problems that have tricked scientists for years. Sleep well, dream deep, and may your unconscious mind wander freely through the mysteries we've explored tonight, through quantum superpositions and cosmic horizons, through turbulent flows and temporal currents, through all the beautiful questions that remind us how much wonder still exists in this universe. Remember, somewhere in the vast expanse of space and time, these mysteries are unfolding, waiting patiently for someone to finally understand them. But tonight, you don't need to solve them. You just need to rest, to let them wash over you like gentle waves, carrying you softly towards sleep. Good night.